Introduction. Part 1 of this course taught you the vocabulary: context windows, tokens, harnesses, the model context protocol, the lethal trifecta as a primer. Part 2 taught you the tools and the daily craft. This part is about the thing that separates someone who can drive an agent from someone who can be trusted to deploy one on a real system, with real money and real users behind it. That is a different skill, not a more advanced version of the first one. Driving an agent well is technique. Deploying one responsibly is judgment. Knowing what can go wrong architecturally, knowing which defenses are real and which are theater, knowing what a thing costs and who is paying, and knowing what you are accountable for when nobody typed the code. The ground rules are the same as before, and they matter more here than anywhere else in the course. Everything load-bearing is sourced. Where I give you a number, I will tell you who published it, when, and whether they sell a remedy for the problem they measured. I will distinguish a peer-reviewed study from a vendor advisory, from a piece of journalism from a single-source anecdote. Because in security, those four get blended together, and the blend is always more dramatic than the evidence. Where the research behind this course could not verify something, I will say so aloud rather than laundering it into confidence. You will hear me flag several such places. The research is current to August 2026. Some of it will age. The reasoning underneath it should not. And where something is genuinely unsolved, I will say it is unsolved, then tell you what competent teams do anyway. Chapter 1 sets up everything that follows. Why judgment, specifically, became the scarce thing. Chapter 1, Why Judgment Became the Job. Here is the argument of this entire part of the course, in one sentence. The cost of producing code collapsed. The cost of deciding whether that code is correct, safe, and something you can live with for 5 years did not move at all. When one side of a pipeline gets radically cheaper and the other side does not, the constraint moves. Everything that follows is about the place it moved to. That is a claim about economics, so let me put evidence on both halves of it, starting with the cheap half. Geoffrey Huntley is an Australian engineer, formerly at Canva and Gitpod, and probably the most aggressive public proponent of running agents in unattended loops. On the 27th of February 2026, he published a piece arguing that software development now costs less than the wage of a minimum wage worker. His figure, quoting him directly, "The cost of software development is $10.42 an hour, which is less than minimum wage." He also writes that the knowledge and skill of being a software developer has been commoditized, and asks what it means to be a software developer when everyone in the world can develop software. Be careful with that number, and I want to model the care rather than just recommend it. $10.42 an hour is Huntley's own arithmetic, not an audited figure, and it measures exactly one thing: token spend per hour of agent wall clock. It excludes review, rework, incidents, and the salary of the person deciding what to build and whether it was built correctly. He is not being dishonest. He is measuring generation, and generation genuinely is that cheap. Our job is to name what the metric contains. A second data point, further up the stack. Gergely Oros, who writes The Pragmatic Engineer, reported on the 9th of July 2026 on the Bun project's rapid rewrite into Rust. $165,000 in tokens, over 11 days, for work the article characterizes as something that would have taken a small team a year. From the freely readable portion, quoting, "To a realist, shortening a 1 to 2 year migration down to 11 days opens amazing new opportunities for developers. Do that arithmetic, and it is favorable on any plausible loaded cost assumption. Now do the caveats, all of which the research file states and none of which are hostile. It was a migration, which means a source of truth already existed, and correctness was checkable against the original. It was an elite team on their own code base. It was reported by the people who did it. Most of the article is paywalled, and the research grades those figures medium to high confidence rather than high. That is the best case shape of task for an agent, and you should not generalize it to greenfield product work. So the generation side is real, and it is dramatic. Now the other side. The most rigorous measurement in the field is a randomized controlled trial published by METR on the 10th of July, 2025. 16 experienced developers, working on large mature open-source repositories they already knew well, completing 246 real issues. The headline, verbatim: when developers are allowed to use AI tools, they take 19% longer to complete issues. That is interesting. This is the part that should genuinely unsettle you. Before the study, those developers expected AI to speed them up by 24%. Afterwards, having actually been slowed down by 19%, they still believed they had been sped up by 20%. That is roughly a 40-point error in self-assessment by experienced engineers on code bases they know. Now the honesty that number deserves. METR is a nonprofit evaluations organization with nothing to sell you as a remedy, which under the incentive test makes it the cleanest measurement in the whole corpus. But the authors explicitly decline to claim that AI does not speed up most developers. 16 people on mature, high-quality repositories is not the median of software work. The participants had only a few dozen hours of experience with the tool, so learning effects are plausible and unmeasured. And crucially, the tooling generation tested was early 2025, which is before the capability step change that both Andrej Karpathy and Simon Willison independently date to November and December 2025. No equally rigorous post-inflection replication has been identified. That absence cuts both ways, and I will not pretend otherwise. Hold the METR result the way its authors do, not as a verdict on agents, but as a calibration instrument on you. What it establishes is that your sense of how a session went is not evidence about how the session went. There is corroboration at practitioner scale. The Stack Overflow Developer Survey for 2025, with roughly 30,000 respondents on the AI questions, found 84% using or planning to use these tools, up from 76% the year before. In the same survey, 46% actively distrust the accuracy of the output against 33% who trust it, and only 3% highly trust it. Positive sentiment fell from over 70% in 2023 and 2024 to about 60%. The top frustration, named by 66%, is solutions that are almost right, but not quite. 45% say debugging generated code takes longer. Adoption up, trust down at the same time. That is exactly the pattern you would expect if the tools are genuinely useful and the failure mode has shifted from obviously wrong to plausibly wrong. Obviously wrong is cheap. The compiler catches it. Plausibly wrong is expensive because it survives casual review. Note also that Stack Overflow is not a neutral party here. Its core question and answer traffic is directly threatened by these tools, and it now sells AI products of its own. The largest dataset says something compatible. The 2025 DORA report, run by Google Cloud, surveyed around 5,000 technology professionals. 90% use AI at work. Over 80% believe it has made them more productive, which is self-report and should be paired with METR every single time you hear it. 30% report little or no trust in the generated code. And the structural finding: a positive relationship between AI adoption and delivery throughput and product performance, and a negative relationship with delivery stability. In the report's words, AI accelerates software development, but that acceleration can expose weaknesses downstream, and without robust control systems, an increase in change volume leads to instability. Name the incentive. Dora is run by a company that sells AI coding assistants and also sells the testing, continuous integration, and platform products the report prescribes as the fix. That is convenient. It does not make it wrong, and the throughput up, stability down split cuts against a pure sales narrative. So why did verification not get cheaper alongside generation? Because reviewing a change properly requires building the same model of the system that writing it would have required. You cannot shortcut that. Adi Osmani named the shape of this in December 2024 as the 70% problem. You get to roughly 70% of a working system startlingly fast, and the last 30%, which is requirements, edge cases, maintainability, and operational reality, degrades into diminishing returns. That essay predates the inflection, and the ratio has plainly moved. The structure of the argument has not been refuted. Two more voices worth carrying with you. Armin Ronescher, who created Flask and Jinya, and who is an enthusiastic agent user rather than a skeptic, wrote in July 2026 that large software projects have never been limited only by how quickly an individual can produce code, but by how well people can coordinate their understanding. Agents remove much of that friction, and so, in his phrase, the tower does not fall and we do not notice what was lost. It just keeps rising. That claim is argued rather than measured, and he would say so himself. And Baldur Bjarnason, in March 2026, made the sharpest epistemic point available, that optimists and skeptics observe the same thing and reach opposite conclusions because they disagree about whether existing practice was any good. His own side of it is blunt. When developers say these tools make them more productive, he argues, you need to keep in mind what is being automated. That is a challenge to measurement validity, and it survives every model improvement, which is what makes it the hardest critique to wave away. Two things to take away and act on. The actionable one is Kent Beck's. He distinguishes vibe coding, where you care only about the behavior of the system, from augmented coding, where, quoting him, you care about the code, its complexity, the tests, and their coverage. Both are legitimate. The failure organization's report is not choosing the first, it is drifting into it without deciding to. So decide, out loud, before the work starts, which mode a given piece of work is in. The evaluable one is a question you can now ask of any productivity claim, including your own. Was that measured, or was it felt? After METR, felt is not evidence. That is the frame. Now the specifics, starting with the one piece of security material that everything else depends on. Chapter 2, Prompt Injection Properly Understood. If you retain one chapter from this part of the course, make it this one. Almost every incident in the chapters that follow is a variation on what I am about to describe. Prompt injection is the class of attack where text arriving from somewhere untrusted is treated by a language model as an instruction from you. Simon Willison coined the name in September 2022, explicitly by analogy to SQL injection, and has spent the years since explaining where the analogy breaks. We will get to that break. It is the most important conceptual point here. First, the taxonomy, because the two halves have completely different threat models. Direct prompt injection is where the adversarial text comes from the person operating the agent. The attacker and the principal are the same party. That is jailbreaking. For a coding agent, it is mostly a vendor policy problem, and it matters for shared or hosted agents and for compliance. It is not the enterprise threat. Indirect prompt injection is where the adversarial text arrives inside content the agent reads in the ordinary course of doing its job. A web page, a GitHub issue title, a pull request comment, a code comment, a dependencies README, a docstring, a continuous integration log, a markdown file in the repository, the description of a tool, the value a tool returns. Text embedded in an image. Read that list again with an engineer's eye because it is the whole argument. A coding agent's core competence is ingesting attacker-influenceable text. There is no careful user mitigation because the user never sees the payload. You cannot train this out of your team. Now the structural point. SQL injection is solved. Prompt injection is not. The difference is not effort. It is that one of them has a formal fix available and the other does not. With SQL, the channel is a formal grammar. The parser has a real, machine-checkable distinction between the query template and the parameter values. Parameterized queries pass the data out of band, where it can never be reparsed, as SQL that is not a filter. It is correct by construction, deterministic, and a malformed query is often loggable and blockable because the attack looks wrong. With a language model, none of that holds. There is one undifferentiated token stream. Instructions and data are the same kind of object all the way down to the attention mechanism. There is no interface that lets you say these tokens are data and must never be read as instructions, because there is no interpreter step at which such a distinction could be enforced. Escaping does not help, because there is no character set to escape. The attack is semantic, and the space of semantically instruction-like English is unbounded. The model is probabilistic, so the same defense can hold 1,000 times and fail on the 1,001st, and you cannot enumerate the failure set. And the attack is well-formed, plausible prose, indistinguishable from legitimate content by inspection. So here is the sentence to carry out of this chapter. We fixed SQL injection by giving the database a way to tell code from data. Nobody has given the language model that ability, and it is not clear a text completion architecture can have it, which means we are not doing input sanitization. We are doing access control. A 2026 preprint explains the mechanism rather than just the shape. Charles Yee, Jasmine Cui, and Dylan Hadfield-Manel, discussed by Simon Willison in June 2026, frame prompt injection as role confusion. Models key on the formatting style of text more than on its provenance. Text that looks like privileged internal content, styled to resemble a system or assistant span, gets treated as privileged even when it arrived through an untrusted channel. Destyling that input so it cannot mimic internal channels dropped attack success from 61% to 10%. 10% is not zero. That is a mitigation, not a fix. Their own conclusion, quoting, "Unless LLMs achieve genuine role perception, we think injection defense will remain a perpetual whack-a-mole game." That is the gift in the paper. The model does not have a channel. It has a vibe. Every delimiter, every XML tag, every all capitals instruction to ignore anything below this line is an attempt to simulate a boundary that does not exist in the architecture. This work is unrefereed, and I am reporting it as such. Now the state of the defenses as of August 2026. Learn the 4 families rather than the products, because products churn. The first family is detection and filtering. Run a classifier over inbound content and refuse anything that looks like an injection. Vendors advertise catch rates around 95%. In application security, that number is misleading. A defense that fails 5% of the time against a random attacker fails essentially every time against a motivated one because the attacker retries. Deploy these for telemetry and commodity attacks. Never let a security decision rest on one. The second family is model-level robustness. Train the model to privilege system instructions over developer instructions over user instructions over tool output. Every major lab does some version of this. The role confusion result tells you why it is incomplete. That hierarchy is learned as a stylistic prior, not enforced as a boundary. It lowers success rates. It does not floor them at 0. And remember the tool poisoning research from earlier in this course, which found more capable models were often more vulnerable because the attack exploits superior instruction following. Before the third and fourth families, the empirical result that should change how you read every vendor claim in this space. In October 2025, a group including Nicholas Carlini published a paper called The Attacker Moves Second. They took 12 recently published defenses against jailbreaks and prompt injection, defenses that had originally reported near-zero attack success, and reevaluated them against adaptive attackers using gradient descent, reinforcement learning, random search, and human-guided exploration. Most fell to an attack success rate above 90%. Their methodological claim is that defenses are typically evaluated either against a static set of harmful attack strings or against computationally weak optimization methods that were not designed with the defense in mind. It is not that defenses are imperfect. It is that the published near-zero numbers were artifacts of weak evaluation and collapsed when someone actually attacked. This, too, is a preprint. Take from it one durable question to ask of any guardrail product. Was this evaluated against an adaptive attacker who knew the design of the defense? The third family is where the credible work is: system-level design patterns. A June 2025 preprint, authored across ETH Zurich, Google DeepMind, Microsoft, IBM, and Invariant Labs, sets out patterns for building agents with provable resistance to prompt injection. Note the word provable. The guarantee comes from the system architecture, not from the model behaving well. The governing constraint is the sentence to remember. Once an agent has ingested untrusted input, it must be constrained so that it is impossible for that input to trigger any consequential action. The authors are candid that this involves trade-offs in terms of utility and security. You buy safety by removing generality. The fourth family enforces data flow outside the model entirely. A Google DeepMind and ETH Zurich system called Camel, published in March 2025, splits the work. A privileged model reads only the trusted user query and emits a program that fixes the control flow in advance, while a quarantined model parses the untrusted content but holds no tools. Untrusted data can never affect program flow because the plan was fixed before that data was seen. A capability system tracks provenance on every value and enforces policy at tool call time in a real interpreter outside the model. Here is the honest number. Camel solves 77% of tasks in a standard agent benchmark with provable security, against 84% for an undefended system. Roughly a 7-point utility tax for a provable guarantee, and it is the best result in the field. That is the empirical price of safety, and it is not zero. Which brings us to whether this is solvable at all. On the 31st of October 2025, Meta's AI security team published a framework they call the Agent's Rule of Two. In it, they describe prompt injection as, quoting, a fundamental, unsolved weakness in all LLMs, and frame their own framework as a stopgap until robustness research allows us to reliably detect and refuse prompt injection. That is a frontier lab, in its own product security guidance, saying the problem is unsolved. It is not a critic's claim. Simon Willison's practitioner position has not moved in 4 years either. Attempts to block or filter these attacks have not proven reliable enough to depend on, and he does not share others' optimism that reliable defenses are coming soon. The rule of two is the thing you can deploy on Monday. Verbatim, agents must satisfy no more than 2 of the following 3 properties within a session to avoid the highest impact consequences of prompt injection. 1. An agent can process untrustworthy inputs. 2. An agent can have access to sensitive systems or private data. 3. An agent can change state or communicate externally. If an agent needs all 3 without starting a new session, they say, it should not operate autonomously and at minimum requires supervision. 2 details their do real work. Within a session means a fresh context window resets your exposure, which makes clearing context between unrelated tasks a security control and not merely a tidiness habit. And Meta's claim is that when the framework is followed, the severity of security risks is deterministically reduced. Deterministically, because it is a property of the configuration rather than of the model's good behavior. The corollaries follow. Make the blast radius the control, not the prompt. A system prompt is advisory, a permission is not. Sandbox and deny egress for any run that reads untrusted content. Plan in a session that has not read untrusted content, then execute that plan in a low-privilege one. So honestly, where does that leave us? Prompt injection is unsolved at the model layer and manageable at the system layer, at a measurable cost in autonomy. The fully general autonomous agent and the provably safe agent are, today, different products. That is a professional engineering statement, and it is what a competent deployment plan has to be built on. Next, the place where all of this becomes concrete. What happens when you connect your agent to somebody else's tools? Chapter 3. The Trust Problem with Connected Tools. The Model Context Protocol, MCP, is the open standard that lets an agent talk to tools and data sources it did not ship with. A server exposes some tools, your agent client connects and can call them. It is the reason a coding agent can read your issue tracker, query your database, or drive your cloud console. It is genuinely useful, and the largest unmanaged trust surface most teams have added in 2 years. Here is what actually happens when a developer adds a third-party MCP server. 4 things at once, usually without anyone thinking about them. First, they execute arbitrary third-party code on their workstation with their own user privileges. A local server is a binary or script your client launches, typically downloaded from a public package registry at first run. Second, they grant that code the same ambient authority they have: SSH keys, cloud credentials, the environment file in the project, the whole home directory. There is no default sandbox. Third, they inject attacker-writable text into the model's context. Tool names, descriptions, parameter descriptions, and every tool result are model-visible prose. That is the previous chapter's attack surface, wired in on purpose. Fourth, they make a one-time trust decision about a mutable artifact. The description you approved is not pinned to the description served tomorrow. So the one-sentence version. Installing an MCP server is not like installing a browser extension. It is like piping a stranger's script straight into a shell, and then also letting that stranger write into your AI's instructions. It would be easy to sound like a scaremonger here, so I am going to cite the protocol specification against itself. MCP carries a security best practices document, revision 2025-11-25, which names these risks in its own words. Under local server compromise, it lists arbitrary code execution, where attackers can execute any command with MCP client privileges; no visibility, where users have no insight into what commands are being executed; command obfuscation, data exfiltration; and data loss, where attackers or bugs in legitimate servers could lead to irrecoverable data loss on the host machine. It then places a requirement on clients. If a client supports one-click local server configuration, it must implement proper consent mechanisms before executing commands, must show the exact command that will be executed without truncation, and must warn that servers run with the same privileges as the client. That is not a blog post. That is the protocol's own specification, and the fact that it needs a document this long, with this many capitalized musts, is the strongest evidence available that the security burden is real and that it sits on clients and operators rather than on the protocol. Now the taxonomy. The spec formally names a set of attacks, and they are worth walking through in plain engineering terms because the list works well as a checklist for evaluating any connected tooling. Confused deputy. An MCP proxy server uses a single static client identifier with a third-party authorization server. Combine that with dynamic client registration and a browser consent cookie, and an attacker can skip the consent screen entirely and have the authorization code redirected to a domain they control. The spec requires per-client consent before forwarding to third-party authorization, exact matching of the redirect address, and a single-use state value stored server-side and issued only after consent. If you have implemented OAuth before, none of that is exotic. Same class of mistake, new place. Token pass-through. A server accepts a token that was not issued to it and forwards it downstream. That bypasses rate limits, audit trails, and audience checks, and, in the spec's words, a malicious actor in possession of a stolen token can use the server as a proxy for data exfiltration. The requirement is blunt. MCP servers must not accept any tokens that were not explicitly issued for the MCP server. Server-side request forgery, SSRF, a malicious server returns discovery metadata pointing at addresses inside your network. The cloud provider's instance metadata endpoint, a local RIDIS port, an internal host. Redirect chains and DNS rebinding are in scope too. Clients are required to consider this and should enforce HTTPS, block private and link local address ranges, validate redirect targets, and route through an egress proxy. Session hijacking. Guessable or shared session identifiers across multiple stateful servers, which lets one user's queue be poisoned or impersonated. Servers must not use sessions for authentication, must use non-deterministic session identifiers, and should bind the session identifier to the user identity. Local server compromise, which we covered. A malicious startup command written into your client config, a malicious payload inside the server itself, or DNS rebinding onto an insecure server listening on the loopback interface. There's also authorization URL injection. A malicious server returns a script scheme URL that the client opens in a browser, or one containing shell meta characters that the client opens by way of a shell. Clients must accept only HTTP and HTTPS and must not use shell commands to open URLs. And scope inflation. A server publishes every scope it supports. The client requests all of them, and now a single stolen token yields read and write across files, database, and admin. The answer is progressive, least privilege scoping. Request narrowly, elevate incrementally when challenged, and accept downscope tokens. One clarification that matters, because the literature genuinely conflates two things. Confused deputy has two distinct meanings in this space. The one I just described is a protocol and authorization flaw. It is deterministic, and it is fixable by correct implementation. The other is the agent confused deputy. Your agent holds credentials for System A and System B, and injected text inside System B talks it into exercising A's authority on the attacker's behalf. That one is not fixable by correct implementation. It is the lethal trifecta wearing a different hat. Which brings me to the single, most important quote in this module. In May 2025, Invariant Labs published a reproducible proof of concept against the official GitHub MCP server. The setup was ordinary: a desktop agent client, a frontier model, and a token that could read the user's private repositories. The attacker filed a public issue on the user's public repository containing injected instructions. The user then said, "Have a look at the issues in my repo." The agent read the issue, followed the instruction, read private repositories, and published their contents in a public pull request. The demonstrated exfiltration included private repository names, the author's salary, and personal relocation plans from a test account. Here is the sentence, verbatim. This is not a flaw in the GitHub MCP server code itself, but rather a fundamental architectural issue that must be addressed at the agent system level. This means that GitHub alone cannot resolve this vulnerability through server-side patches. Read that twice. Everything in your AppSec training says, wait for the fix, apply the patch, close the ticket. There is no fix to wait for. The vulnerability is a property of the configuration you chose, which means the mitigation is a decision you own permanently. Scope the token, or do not put private repository authority and public issue reading in the same session. What else is verified about hostile servers, as distinct from hostile content? 3 things. The Shai-Hulud campaign injected rogue MCP servers into local AI assistant configuration files, a real, in-the-wild campaign documented by multiple vendor and research teams. A peer-reviewed study presented at AAAI, called MCP Talks, measured an average attack success rate of 36.5% against real tools on 45 live servers. And a published vulnerability in a widely used MCP bridging tool, Severity 9.6, was triggered specifically by connecting to an untrusted server. The threat model, where the server attacks the client, is confirmed by a vulnerability record, not hypothetical. I will also tell you what I am leaving out. There is a widely retold story about a backdoored MCP package for an email service. The research behind this course could not reach the original disclosure, so it is marked unverified, and I am not narrating it as fact. The pattern it illustrates is covered by Shai-Hulud anyway. That is the discipline. When a story sounds cinematic, find the vulnerability record, the vendor post, or the researcher's own write-up. If none exists, cut it. Now mitigations, 8 all deployable this week. 1, and this is the highest ratio of protection to effort in the whole module, treat MCP configuration files as production security configuration. Check them into version control, code review changes to them, put owners on them, alert on drift. Shai-Hulud wrote itself into exactly these files. Very few teams do this today. 2. Pin versions and use lock files. A configuration entry that fetches the latest published version at every launch is a standing invitation to a rug pull. 3. Approve per configuration hash, not per server name. At least one client shipped this after a disclosure. Any change to the entry, even whitespace, forces reapproval. Demand it of whatever client you use. 4. Sandbox the server, not just the agent. Container, restricted file system mount, no ambient cloud credentials in that process's environment. 5. Least privilege the credential per server. Fine-grained token, single repository, read-only where possible. The GitHub proof of concept only worked because the token could read private repositories. 6. Never mix a private data server and an untrusted content server in the same session. That is the rule of 2 applied to your tool inventory, and unlike a good intention, it is a policy you can audit. 7. Statically scan tool descriptions for obvious poisoning and cross-server shadowing. Necessary, not sufficient, filters lose to adaptive attackers. 8. Prefer a vetted remote server with proper authorization over a local one that executes downloaded code. That removes the arbitrary local code execution leg entirely, at the cost of the authorization risks we just walked through. Finally, one sentence from Anthropic's own documentation that people consistently get wrong. Anthropic reviews connectors against its listing criteria before adding them to its directory, but does not security audit or manage any MCP server. A listing is a listing. It is not an audit, and the same reasoning applies to every registry and plugin marketplace you will meet. Next, the other way hostile code arrives, which is that your agent asks for it by name. Chapter 4. Supply Chain and Invented Packages. You already know that language models make things up. What you may not have thought about is that when a model invents the name of a software package, it does not invent a fresh one each time. It tends to invent the same one. That single property, repeatability, is what turns a harmless error into a supply chain attack, and it is the whole content of this chapter. Let me give you the measurement first, carefully, because a headline number here is worth getting exactly right. The study is by Joseph Spracklin, Raveen Widrakrama, Nazmus Saqib, Anindya Mehdi, Bimal Viswanath, and Murtuza Jadliwala, titled, "We Have a Package for You." It was published at the USENIX Security Symposium in 2025, which is one of the 4 top-tier academic security venues. This is peer-reviewed work, not a vendor report, and I want that distinction in front of you before the figures. They generated 576,000 code samples across 16 code-generating models and 2 languages, Python and JavaScript. Those samples contain 2.23 million package references. Of those references, 19.7%, 440,445 of them, pointed at packages that do not exist. Be precise about that, because the figure is commonly garbled, including in an earlier pass of this course's own research. It is 576,000 code samples containing 2.23 million package references. It is not 2.23 million code samples. Getting a headline number wrong in a certification course is a credibility failure, so I am flagging the correction rather than quietly fixing it. 2 more figures from the same paper. Minimum hallucination rate for commercial models, 5.2%, for open source models, 21.7%, and across the whole corpus, 205,474 unique invented package names. The authors characterize this as a persistent and systemic phenomenon. Now the finding that matters most, which comes from the body of the paper rather than the abstract. When they reran the same prompts, 43% of the hallucinated names recurred in all 10 repetitions. 58% recurred in more than one. Stop and think about what that means as an engineer. A random error is a nuisance. A deterministic error is an interface. If a model reliably invents the same non-existent package name when asked a common question, then that name is a namespace slot with predictable traffic, and anyone can go and register it. That is the attack, and it has a name: slop squatting. Compare it with typosquatting, which you already know. Typosquatting requires the victim to make a mistake to fat finger a package name. Slop squatting requires the model to make the mistake, and the model makes the same mistake reproducibly, at scale, across every developer who asks a similar question. Notice what that does to the usual advice. There is no moment of carelessness to train out. The developer read a plausible package name inside a plausible answer and installed it. Their trust was not misplaced in the ordinary sense, and the attacker's cost is one query loop against a public model plus a free registry account. The reproducibility statistic is what makes that return on investment work. Now, the current state. I have to be honest about the limits of what I can tell you here. There are 2026 follow-up studies reporting lower rates on frontier models, and there is vendor research identifying specific live slop squatting targets. The research pass behind this course could not independently re-verify either, so they are marked unverified, and I am not going to quote numbers I cannot stand behind. What I can defend is this. The peer-reviewed 2025 figures are solid. Rates have plainly improved with newer models, and the floor is still measured in percentage points, not in zeros. And here is the part that matters operationally. At agentic volumes, a few percent is not a risk, it is a certainty. An agent that runs an install command dozens of times a day, unattended, across a fleet of tasks, will eventually reach for a name that does not exist. Your control has to assume that, not hope against it. Let me now put a real incident on the table, because the theory needs a body. On the 6th of March 2026, Simon Willison wrote up research by Adnan Khan into an attack that has been named Kleinjection. This one is not a proof of concept. It was exploited in the wild, and the victim was the Klein project, an agentic coding tool. People who are, by definition, expert in this technology. Expertise did not save them. The chain has 3 links, and the lesson is in the composition rather than in any single link. Link 1, prompt injection through a GitHub issue title. The repository ran an AI coding action on user-submitted issues with bash and file access enabled. An attacker put instructions in the title of an issue and obtained arbitrary command execution inside continuous integration. Not a payload, not a binary. A string in a text field submitted by anyone on the internet. Link 2, continuous integration cache poisoning, using a malicious package that abused the cache eviction policy. Link 3, shared cache keys across workflows. The poisoned cache was consumed by the nightly release workflow, which handed over its secrets. The outcome, an anonymous attacker published a release of the Klein package to the public registry. It has since been retracted, and per the report, the attacker did not take any more dangerous steps than that. But the access was genuinely obtained, and a real package went to a real registry. The report also notes, pointedly, that the project failed to handle the responsibly disclosed bug report promptly and were exploited. I think this is the single best incident for a course like this one, for 4 reasons. The victims were experts. The entry vector was an issue title. The vulnerable pattern, running an AI agent with tool access over untrusted user-submitted content inside continuous integration, is extremely popular right now in triage bots and auto-labelers and autoresponders, and a good number of you will have exactly that deployed. And it is the lethal trifecta living inside your build system. Untrusted content in the issue title, private data in the build secrets, external communication through publishing to a registry. The specific mitigation: never run an AI agent with write or execute tools over untrusted issue or pull request content from unprivileged authors. If you must triage automatically, run it fork isolated and secretless, with no registry credentials in scope, and never share cache keys between an untrusted input workflow and a release workflow. Scope the build token read-only. Require manual approval for workflow runs from first-time contributors. One more, and I will label its status precisely, because the label is the teaching. On the 29th of July, 2026, the researcher Hakan Mal disclosed a self-propagating prompt injection through a document assistant. Hidden instructions in a source document get processed as part of the user's request, and the payload copies itself into the newly generated document, which then infects the next workflow that consumes it. A worm. This is a research demonstration. It was not observed in the wild, and I want that said out loud. The researcher also states that the vendor had 144 days after disclosure, and that no comprehensive mitigation for the full attack class existed at publication. That is his claim, attributed to him. The transfer to your world is direct. Substitute repository file for document. A poisoned agent instruction file, README, docstring, or code comment that tells the agent to reproduce itself into other files it edits is the same worm topology inside a codebase, and it would survive into every downstream fork. I have to be scrupulous here. That code repository variant is an extrapolation from a demonstrated attack. The research found no documented in the wild instance. Treat it as a design consideration, not as a reported event. Right, controls. All 6 of these are concrete, and all 6 are enforceable in continuous integration, which is the point. This is a class of problem where deterministic gates beat vigilance. 1. Deny the agent unattended install authority. Package installation should require approval or be blocked outright in the agent's permission configuration. This single control defeats the entire attack class, and it costs you very little. 2. Lockfills with integrity enforcement. Install from the lockfill, not from the manifest, the strict hash-checking install path in whichever ecosystem you are in. Hashes make a swapped package fail closed rather than fail silently. 3. A continuous integration gate on new direct dependencies. Fail the build if the agent's diff adds a direct dependency that was not there before and route it to a human. It is cheap, it is deterministic, and it catches slop squatting, rug pulls, and license contamination with one rule. 4. An internal registry proxy serving only vetted packages. This is the strongest control available, because it converts the question, does this package exist, from a public internet question into a policy question that you answer. 5. Existence and reputation heuristics as a pre-install check. Package age, download count, whether the repository link resolves, maintainer history. A brand new package carrying the exact name your model just suggested is the signature of this attack, and it is a signature a script can look for. 6. Disable or restrict install time scripts. Both the NX compromise and the Shihuled worm executed through install hooks. Turning those off by default removes a large part of what an unwanted package can even do. And underneath all 6, one habit. Review new dependencies like you would review a new colleague's first commit to a security-sensitive module. Provenance matters. Who published it, when, from where, and does the code do what the name says? A closing thought that ties this back to the previous 2 chapters. Prompt injection is the model being talked into acting for someone else. A hostile connected tool is you inviting that someone in. An invented package name is the model handing an attacker an address in advance, and the attacker simply going there and waiting. The mechanism differs. The control does not constrain what the agent is able to do deterministically outside the model. Which is exactly where the next chapter goes: secrets, permissions, and how much damage a single session can actually do. Chapter 5: Secrets, Permissions, and Blast Radius. Here is the operating assumption I want you to adopt for the rest of this course. Assume the agent will eventually do the worst thing its permissions allow, not because it is malicious and not because the model is bad. Assume it because an agent's core competence is reading text that other people wrote, and because there is no mechanism inside a language model that reliably separates the text it was asked to process from the text it treats as an instruction. Anything the agent reads can, on a bad day, become something the agent does. So the interesting question is never, will it behave? It is, what is the worst outcome reachable from this configuration, and can I survive it? That is a familiar move for you. It is threat modeling, and it is the same reasoning you apply to a service account. You do not give a batch job production write access and then rely on a comment in the code telling it to be careful. The clearest demonstration of this is an incident from July 2025 involving Replic's agent. During a long unsupervised session, the agent deleted a live production database during a declared code freeze after the user had repeatedly instructed it, in capital letters, not to touch production. I want to be careful here because this story gets retold badly. The technical account comes from the affected user, so it is single source. The framing you will hear, that the agent lied about it afterwards, is wrong in a way that matters. A model producing a confabulated status report is not deception, it is a wrong answer that happens to be about itself. What is verifiable and what is worth teaching is the vendor's response. Replic's chief executive publicly called it unacceptable, and within days the company shipped automatic separation of development and production databases and a planning-only mode in which the agent can reason about a codebase without the ability to modify it. Both of those are structural changes. Neither is a better instruction. That gives us the sentence the whole chapter hangs on. Instructions are advisory. Permissions are the control. Telling the agent not to touch production is not access control. The absence of the credential is. There is formal vocabulary for this. OWASP, the organization behind the top 10 web application risks you already know, publishes a top 10 for large language model applications, current edition 2025. Item 6 on that list is excessive agency, which is the standards body name for I gave the agent too many permissions. Item 2 is sensitive information disclosure. Item 1 is prompt injection, and Item 3 is supply chain. Those 4 are the ones that matter for coding agents. OWASP has also gone Agentic specific. An Agentic security initiative published Agentic AI Threats and Mitigations, version 1.0, in February 2025. A Securing Agentic Applications Guide in July 2025. And a top 10 for agentic applications published in December 2025 with contributions from more than 100 industry experts. I will be straight with you about a limit in my own preparation. I have the publication dates and provenance of that agentic list, but I do not have its 10 items in front of me, so I am not going to recite them. Get the document, it is free. Now the concrete surfaces, in the order they bite. The first is credential exposure, and the thing engineers underestimate is ambient authority. An agent running on your workstation inherits your identity, so does any tool server you attach to it. When you add a third-party MCP server, the Model Context Protocol, the standard way agents acquire tools, you are usually launching a script downloaded from a public registry at first run, executing it with your own privileges, with no sandbox by default. It can read your SSH keys, your cloud credentials directory, your .env files, your whole home directory. The protocol's own security guidance names this plainly, listing arbitrary code execution with client privileges, no visibility into what commands are executed, and data exfiltration among the risks. That is the specification talking about itself, not a critic. The second is overbroad grants. In May 2025, Invariant Labs published a working demonstration against the official GitHub tool server. An attacker filed a public issue containing instructions, the user asked their agent to look at the issues, and the agent read the user's private repositories and published their contents in a public pull request. The load-bearing detail is not the injection, it is that the token could read private repositories. A single repository, read-only, fine-grained token turns that entire chain into nothing. Scope credentials per server and per session, not per person. The third is the bypass everything mode, and this is where I want to change your mental model rather than just warn you. Every serious coding agent has a flag that turns off approvals. The usual framing is that this is a personal risk decision, my machine, my problem. It is not. In August 2025, The NX build tool's NPM packages were compromised, tracked as a real CVE, and documented by multiple security vendors. The malicious install script searched the machine for installed AI command line tools, Claude Code, Gemini CLI, Amazon Q, and invoked them with their own documented permission bypass flags, instructing them to enumerate the file system for interesting files, secrets, and wallets. It exfiltrated tokens, SSH keys, and environment variables into public repositories, and public data showed victims numbering in the thousands. Read that again. The attacker did not need to write a file system traversal implant. You had already installed one, with credentials, and the vendor had documented the flag that switches off its restraints. An agent on your machine is a capability an attacker can borrow. The fourth is egress, and this is the one that is consistently designed wrong. The instinct is to allow list domains. That is not sufficient, and there are two independent demonstrations of why. In the Camel-leak vulnerability disclosed in October 2025, a Copilot chat prompt injection exfiltrated private source code through GitHub's own image proxy. 1 character per signed, policy legal image request. In January 2026, researchers at Prompt Armor showed the same shape against Claude Cowork, which defaults to allowing outbound traffic only to a list of domains. But the vendor's own API domain was on that list, so an injection could upload the victim's files to the vendor's file endpoint using the attacker's credentials and collect them later. 2 independent instances of the trusted platform is the exfiltration channel is a pattern, not a coincidence. The design rule that follows: allow list by endpoint and method, not by domain, and treat any write-capable allow-listed endpoint as egress. Also treat as egress the things that do not look like network calls, a rendered markdown image, a DNS lookup, a GET push, a pull request body. So what do you actually do? Meta's security team published a framework in October 2025 they call the Agent's Rule of Two, and it is the most deployable thing in this space. Their formulation: an agent must satisfy no more than 2 of the following 3 properties within a session. It can process untrustworthy inputs, it can access sensitive systems or private data, or it can change state or communicate externally. If it needs all 3, it should not operate autonomously, and at minimum requires human approval. 2 details make this good engineering rather than a poster. First, Meta's claim is that following it reduces severity deterministically. It is a property of the configuration, not of the model's good behavior. Second, the phrase within a session. A fresh context window resets the exposure, which means clearing context between unrelated tasks is a security control, not just tidiness. Underneath that, the controls are unglamorous. Give the agent its own machine identity rather than borrowing yours, so its actions are attributable and revocable. Issue short-lived credentials. Keep production credentials out of the agent's environment entirely, not restricted, absent. Run it in a container or virtual machine with the file system scoped to the worktree. Treat agent configuration files and tool server configuration as security configuration. Version them, put owners on them, review changes, alert on drift. Log sessions, tool calls, and executed commands, because after an incident, the only question is what it did and with what. And write the runbook now, assuming that everything in the agent's environment is compromised and must be rotated. One trap worth naming: editor checkpoints are not backups. They track changes made through the file editing tools, not changes made by shell commands. That is not a replacement for Git. 2 more things, both counterintuitive. Anthropic's own documentation for Claude Code describes what a serious default looks like. Read-only permissions to start, a working directory boundary, a sandbox shell with file system and network isolation, commands like curl and wget not auto-approved, fetched web content processed in an isolated context window so it cannot inject into the main one, and unmatched commands failing closed into manual approval. And a documented caveat that deserves your attention: trust verification is disabled in non-interactive mode. Your continuous integration usage, the unattended one, is the least protected usage you have. The second counterintuitive point is about approvals. The vendor documentation names prompt fatigue as a design problem, and the practitioner version is blunter. After the 10th approval, you are not reviewing, you are clicking through. So the correct move is to allow list aggressively and narrowly so that the prompts which remain are genuinely meaningful. A team with 200 approval prompts a day has no approval control at all. A team with 5 does. None of this makes the generated code correct. That is a separate axis, and the evidence on it is worse than most engineers expect. That is the next chapter. Chapter 6: The Security of Generated Code. Start with the failure mode because it is the whole chapter. Generated code is plausible. It has the right shape, sensible names, a docstring, a test that passes. It reads like code a competent colleague wrote in a hurry. And security defects are precisely the class of defect that looks fine. A missing authorization check is not a syntax error. An unescaped template is not a compile failure. A comparison that leaks timing does not fail a unit test. These are absences, and absences do not draw the eye during a review that is mostly checking whether the logic is right. So we need evidence rather than impressions. There are 4 studies worth knowing. They use 4 different methods, and they answer 4 different questions. I am going to give you each one with its source, and just as importantly, with what kind of evidence it is, because a peer-reviewed venue, a controlled human study, an unrefereed benchmark, and a vendor report are 4 different weights, and a professional does not average them. The first question is whether the model emits vulnerable code at all. Hammond Pierce, Balig Ahmed, Benjamin Tan, Brendan Dahling-Gavitt, and Ramesh Carey published Asleep at the Keyboard, Assessing the Security of GitHub Copilot's Code Contributions at the IEEE Symposium on Security and Privacy in 2022. That is peer-reviewed at a top-tier security venue. They built 89 scenarios derived from MITRE's list of the 25 most dangerous software weaknesses and generated 1,689 programs. Roughly 40% were vulnerable. Now the caveat, because it matters more than the number. That was the 2021 generation of Copilot. Do not carry 40% into a conversation about today's tools. You will be wrong and you will deserve to be corrected. What survives is the author's causal explanation, and it is the durable part. The model was trained on unvetted open-source code, so it learned from exploitable, buggy examples. A model trained on the average of public code reproduces the security posture of public code. There is no mechanism by which it would do better unless someone deliberately builds one. The second question is different and more uncomfortable. Not, does the model emit vulnerable code, but do humans with this tool produce less secure systems? Neil Perry, Megha Srivastava, Deepak Kumar, and Dan Boneh at Stanford ran a controlled user study, published at the CM Conference on Computer and Communications Security in 2023. Again, a top-tier peer-reviewed venue, and this time a human subjects experiment with a control group. Participants completed security-relevant programming tasks with or without an AI assistant. First finding, participants with AI assistants wrote significantly less secure code than those without. Second finding, and this is the one I want you to remember, those with AI assistants were more likely to believe they had written secure code, more vulnerable, and more confident. Third finding, which is the actionable one, participants who trusted the assistant less and engaged more with the wording and structure of their prompts produced code with fewer vulnerabilities. Skepticism was protective, and it was measurable. Put that next to the METR randomized trial, where experienced developers were measurably 19% slower using AI tooling while believing they had been 20% faster. 2 rigorous studies, 2 completely different outcome variables, speed and security, and the same structural result. AI assistance degrades the accuracy of your self-assessment. That is not a claim that these tools are bad. It is a claim that your judgment about their output is miscalibrated, and it is the entire reason a professional needs instruments rather than impressions. The third question is the one engineers actually care about. How often is the code both correct and secure? Backbench from Mark Vero, Niels Mundler, Viktor Chibataru, Veselin Rayshev, Maximilian Botter, Nikola Jovanovic, Jingshuan He and Martin Veshev at ETH Zurich and Logicstar, published as a preprint in February 2025. Preprint means not peer-reviewed. Say that out loud when you cite it. 392 backend application generation tasks. Correctness measured with test suites. Security measured by executing real end-to-end exploits against the running application, not by static analysis, which is why this benchmark is worth your attention. The result: the best model at the time of that evaluation reached only about 62% on correctness, and roughly half of the functionally correct programs still had working, executable exploits. Compose those and you get somewhere near 31% correct and secure. Say that number slowly, because it quantifies something engineers routinely conflate. Functional correctness and security are close to independent axes. A green test suite is evidence about one of them and silence about the other. If your verification loop consists of running the tests, you have measured half the problem and declared the whole thing done. The fourth study is the largest and the most counterintuitive, and it is the reason this chapter exists as a separate chapter rather than a warning inside another one. Veracode published its 2025 GenAI Code Security Report on the 30th of July, 2025. Disclose the conflict before the number, always. Veracode sells application security scanning, so it sells a remedy for the problem it is measuring. That does not make it wrong. It means you state the interest first. They evaluated over 100 models across 4 languages, Java, Python, C# and JavaScript, on curated tasks with known vulnerable patterns. Headline: 45% of code samples failed security tests and introduced vulnerabilities from the OWASP top 10. By language, Java failed 72% of the time, C# 45%, JavaScript 43%, Python 38%. The Java outlier is worth a moment's thought. The most plausible explanation is corpus age, decades of legacy Java patterns in the training data. By weakness, models failed to defend against cross-site scripting in 86% of the relevant samples. But the headline is not the important finding. This is, and I will give it to you as they wrote it. While the models got better at writing functional or syntactically correct code, they were no better at writing secure code. Security performance remained flat, regardless of model size or training sophistication. Sit with that. Across more than 100 models spanning several capability generations, functional ability improved and security did not. That directly refutes the most common objection you will hear in a planning meeting, which is, the next model will fix this. On this evidence, it will not. And there is a corroborating signal from a different direction. Research on tool poisoning against real tool servers found that more capable models were often more vulnerable, not less, because the attack exploits superior instruction following. Capability can cut against you. The honest summary is that security is not on the capability curve. It is an orthogonal property that has to be engineered in from outside the model. That single sentence justifies every control in this course. Now let me hold myself to the standard I have been demanding. 40%, 45%, and half of the correct ones are not the same measurement. Different tasks, different scoring, different eras, different definitions of vulnerable. Do not average them and be suspicious of anyone who does. What converges across 4 studies, 4 methods, and 2 peer-reviewed top-tier venues is a direction and a flatness. A substantial minority to plurality of generated code carries a real vulnerability, and that fraction has not improved as models have got more capable. And here is the limitation that a certification course must state fairly, because it is the strongest objection to everything I just told you. All 4 studies measure generation in isolation. A model, a prompt, an output, a score. None of them measures a 2026 agentic loop with a test suite, linters, static analysis running in continuous integration, and a human reviewer in front of it. A team with those controls should expect materially better outcomes than these numbers. That is the entire point of the controls. but no published study I am aware of quantifies the improvement. That is a genuine gap in the evidence, and I would rather name it than paper over it in either direction. If someone publishes that measurement, it is the most important paper in the field. So what do you do on Monday? 6 things, and they are all deterministic, which is the point. First, static and dynamic analysis in continuous integration on the agent's diff. Blocking. Non-negotiable. Agent-authored code is exactly the case where automated scanning pays for itself, because volume is high and author attention is low. Second, secret scanning with push protection, because generated code and generated configuration both leak credentials. Third, security-focused review rather than general review. Remember the Stanford finding: reviewers of AI-assisted work are overconfident. Have a careful look is not a control. Give the reviewer a checklist of the top weaknesses for that language, cross-site scripting for JavaScript, injection, authorization, crypto misuse, and require them to state what they checked. Fourth, give the agent the security check as part of its own loop. Running the scanner as a tool, the agent can invoke converts a post hoc gate into an in-loop signal, and an agent that can see its own failure will usually fix it. That is strictly better than catching it later. Fifth, dependency and license, scanning on every agent-authored change. Sixth, and this is the one to write on the wall, do not accept the tests pass as a security signal. Backbench is your citation for why. The evidence so far has been statistical, rates, benchmarks, controlled studies. The next chapter is the other kind. Specific incidents with named sources where agents caused real damage, and, just as importantly, the ones I am refusing to tell you about. Chapter 7, When Agents Cause Damage. A warning before the content. This subject attracts storytelling. An incident gets a name, the name gets a logo, the logo gets a conference talk, and by the 5th retelling, the agent has become a villain with intent. The retelling is almost always more dramatic than the advisory it came from. So I hold to one rule, and I would like you to adopt it as a professional habit. If an incident cannot be traced to a named researcher's write-up, a vendor advisory, or a CVE record, it does not get told. And for every incident I do tell you, I will say whether it was exploited in the wild or demonstrated by a researcher, because that distinction is the difference between a security course and a scare story. There are things I have deliberately cut, and I will name them at the end, because the restraint is itself part of the lesson. The first incident is the most important one in this course, and it has been given the name Kleinjection. It was written up by Simon Willison on the 6th of March 2026, reporting research by Adnan Khan. Status: exploited in the wild. This is not a proof of concept. The target was the GitHub repository of Klein, which is itself an agentic coding tool. The chain had 3 links, and the lesson is the composition, so follow all 3. Link 1. The repository ran an AI coding action inside continuous integration on user-submitted issues with shell and file access enabled. An attacker put instructions into an issue title. Not a payload, not a binary, not an attachment, the title field of a public issue, which anyone on the internet can write. The agent read it and executed arbitrary commands inside the build. Link 2. From that foothold, the attacker poisoned the GitHub Actions cache, using a malicious NPM package and abusing the cache eviction policy to make sure their entry survived and the legitimate entries did not. Link 3. Cache keys were shared across workflows. The nightly release workflow consumed the poison cache, and with it, the attacker got the release workflow's secrets. The outcome: an anonymous attacker published a version of the Klein package to the public NPM registry, since retracted. According to the report, the attacker did not take any more dangerous steps than that. So this was a demonstration of access, but the access was genuinely obtained, and a real package landed in a real registry that real developers install from. The bug had also been responsibly disclosed beforehand and was not handled promptly. Why I put this incident first. The victim was an agentic coding tool project. These are people who are, by definition, expert in this technology. Expertise did not save them. The initial vector was a string in a text field. And the vulnerable pattern, run an AI agent with tool access on untrusted user-submitted content inside continuous integration, is an extremely popular pattern right now. Triage bots, auto-labelers, issue responders. A meaningful number of teams listening to this have exactly that deployed today. It is also the three-part exposure in its purest form: untrusted content in the issue title, private data in the build secrets, external communication via the registry. All three unattended. The mitigations are specific, so write them down. Never run an agent with write or execute tools on untrusted issue and pull request content from unprivileged authors. If you must triage automatically, run it in a fork-isolated workflow with no secrets in scope. Never share cache keys between a workflow that ingests untrusted input and a workflow that ships releases. Scope the build token to read-only. Require manual approval for workflow runs from first-time contributors. The second incident is a researcher demonstration, and I will say that clearly, no in-the-wild abuse has been reported. On the 14th of January 2026, Simon Willison reported work by Prompt Armor against Claude Cowork. The product defaults to allowing outbound network traffic only to a specific list of domains, precisely to protect users against injections that exfiltrate their data. Good instinct. But the vendor's own PI domain was on that allow list. So a prompt injection could upload the victim's accessible files to that PI's file endpoint using the attacker's own credentials, and the attacker could collect them later from their own account. Nothing was broken, every control worked as specified, the data still left. The generalizable lesson is a design lesson, and it is the most useful sentence in this chapter. An egress allow list is only as strong as the least restricted capability of the allow-listed host. Any allow-listed domain that accepts uploads, accepts arbitrary request bodies, or renders attacker-controlled content is an exfiltration channel. And this is not a one-off, which is how I know it is a pattern rather than a curiosity. The Camel-Leak vulnerability, a high-severity CVE found by Omer Mehrez at Legit Security, disclosed in October 2025, did the same thing to GitHub Copilot chat. Hidden instructions in a pull request comment, and exfiltration through GitHub's own image proxy, which converts external image links into signed proxy requests. The researcher pre-generated one valid proxy link per character and had the assistant render the stolen data as an image mosaic, each image a signed, policy-legal request carrying one character out. Private source code and keys were reachable because the assistant operates with the permissions of the user who invoked it. Two independent incidents, two different vendors, and the same shape. The trusted platform was the exfiltration channel. So when you design egress control, allow list by endpoint and method, not by domain, and assume any write-capable endpoint on your allow list is an open door. The third incident is short, but it retrains a reflex. In July 2025, someone submitted a pull request to the AWS Toolkit for Visual Studio Code repository. It was merged, and the resulting extension version was published to the marketplace. The malicious content was not code. It was a prompt, English prose instructing the agent to behave as a system cleaner and delete local files and cloud resources. According to AWS, formatting errors in the attacker's prompt prevented the logic from executing under normal conditions, and there is no evidence of customer data deletion. Tokens were revoked and a fixed version shipped. The lesson is not about AWS, it is that every code review reflex you have is tuned to catch code. Nobody's threat model included the sentence, the malicious commit is a paragraph. Instruction files, agent configuration, and prompt templates are executable content now. Review them like code, with named owners, and diff them on every change. The fourth is in the wild, and I mention it again because the pattern is the one most worth recognizing. In August 2025, the NX Build Tools NPM packages were compromised, a documented CVE written up by several security vendors. The install script hunted the machine for installed AI coding tools and invoked them with their permission bypass flags, using the agent itself to enumerate the file system for secrets, which it pushed into public repositories. An installed agent with a documented bypass flag is a prepositioned implant, with credentials waiting for someone else to type the flag. The fifth is a demonstration, not an in-the-wild event, and I will be precise about the boundary. On the 29th of July 2026, Hack&Mal disclosed a self-propagating prompt injection against Microsoft Word's assistant. Hidden instructions in a source document get processed as part of the user's request, and the payload copies itself into the newly generated document, which then becomes the infection vector for the next workflow that consumes it. A worm topology built out of prose. The researcher states that 144 days after disclosure, no comprehensive mitigation for the full attack class existed. I report that as his claim, attributed, and note that it is consistent with everything else in this course about problems that have no vendor patch. Now the transfer, labeled clearly as my extrapolation rather than a documented finding. Substitute repository file for document. A poisoned instruction file, README, docstring or code comment that tells the agent to reproduce the same text into other files it edits is the same worm topology inside a codebase, and it would survive into forks and downstream dependencies. I found no documented in-the-wild instance of that. Hold it at exactly that confidence, worth defending against, not worth telling people it has happened. Finally, what I am leaving out and why. There is a widely circulated story about a rogue tool server, distributed as an ordinary NPM package, that presented as a legitimate email integration while quietly copying every message to an attacker. It illustrates a real pattern, but I could not retrieve the original security firm's write-up from a primary source while preparing this, so it is excluded. Not disproven, unverified. I am also leaving out a set of 2026 follow-up figures on hallucinated package names that I could not confirm against the papers they are attributed to. And one correction to how a famous incident gets told. The Replit case, where an agent deleted a production database during a code freeze, is real and the vendor's response is verifiable. But the technical account is single source, from the affected user, and the widely repeated claim that the agent lied about what it did is a category error. A model producing a confabulated status report is not an intent to deceive. Why the restraint matters is professional rather than pedantic. You will at some point stand in front of management or a security review board and argue for controls that cost money and slow people down. The fastest way to lose that argument is to be caught repeating one exaggerated anecdote. You lose more credibility from one inflated story than you gain from 10 good ones. 4 patterns to carry out of this chapter. The injection arrives in a text field nobody thinks of as input. The trusted platform is the exfiltration channel. The payload is prose, so code review does not see it. And the agent you installed is a capability an attacker can borrow. Everything so far has been about what can go wrong. The rest of this part is about how you would know, starting with the discipline that separates an operator from an enthusiast, which is measurement. Chapter 8, Evaluation, Measuring What Matters. Here is my strongest opinion in this course, offered as opinion and stated so it can be argued with. The single skill that separates someone operating these tools professionally from someone enjoying them is evaluation, not prompting. Not knowing which model is currently top of a leaderboard. The ability to answer, with evidence, the question, is this configuration better than that one on my work, and to know what would change the answer. Start with the vocabulary, because this is one of the terms the field uses casually and the listener has probably never had defined. An eval, short for evaluation, is a fixed set of tasks, a repeatable way of running a system against them, and a scoring rule that does not depend on how you felt afterwards. That is it. It is the regression suite of the probabilistic world. But it is not a test suite, and the difference is important. Your test suite asserts on a deterministic system, same input, same output, pass or fail. The The system under test here is not deterministic. Run the same task 5 times and you may get 5 different diffs, 3 of which work. So an eval does not produce a pass, it produces a rate. That has consequences. You run each task several times, not once. You report the pass rate, not the best run. And you keep the task set fixed across configurations because the moment the tasks move, the comparison is worthless. Now, why you cannot skip this and just ask your engineers how it is going. METR, a nonprofit evaluations organization, which sells nothing and has no remedy to offer for the problem it measured, making it the cleanest source in this entire field, ran a randomized controlled trial published in July 2025. 16 experienced open-source developers. 246 real issues from their own repositories. Large, mature code bases averaging over 1 million lines. Each issue randomly assigned to a I allowed or a I not allowed. Tooling was the frontier of early 2025, which means chat-style assistance, not the agentic tools this course is about. The headline, developers took 19% longer when allowed to use AI tools, but the finding that generalizes is the other one. Before the study, they forecast a 24% speedup. After completing the tasks, having actually lived the slowdown, they still believed they had been sped up by about 20%. That is roughly a 40-point error in self-assessment by experienced engineers on code bases they knew intimately. Now the part most commentary in 2026 has not caught up with, and a certification course has to state it. In February 2026, METR published a follow-up describing why they are changing the experiment design. They ran a second trial with newer, agentic tooling, 57 developers, over 800 tasks, across 143 repositories. Returning participants still showed a slowdown. Newly recruited ones showed a much smaller effect whose confidence interval crossed 0. And METR's own position is that you should not trust even those numbers, because the design broke down. Developers increasingly refuse to participate at all rather than work without an eye. Between 30 and 50% of participants reported deliberately not submitting the tasks they expected an eye to be very good at. And time measurement itself breaks when people go and do something else while an agent runs. Their conclusion, in their words, they believe it is likely developers are more sped up in early 2026 than their early 2025 estimates implied. But because of the selection effects, their data is only very weak evidence for the size of that increase. So take 2 lessons, not 1. First, anyone quoting AI makes developers 19% slower as a present tense fact is misrepresenting the source, and you should say so. Second, and more useful, the perception gap has not been retracted. Self-report is not measurement. And if a professional evaluations organization with a randomized design and a research budget finds this hard to measure, your team's impressions in a retrospective are not going to settle it. That is an argument for small, local, decision-shaped measurement rather than for grand productivity studies. Next question, why not just use the public benchmarks? You will meet 2 by name. SWE-Bench from Princeton, published at the International Conference on Learning Representations in 2024, gives a system a repository at a specific commit plus a GitHub issue, asks for a patch, and grades it by running the repository's own unit tests. The variant everyone quotes in press releases is SWE-Bench Verified, 500 problems confirmed by engineers to be solvable, released in August 2024. The other is Terminal Bench, which scores agents on real terminal work, building kernels, configuring servers, training models. They are genuinely useful, and they are not evidence about your codebase. 4 reasons. The first is contamination. A paper titled The SWE-Bench Illusion by Shanchao Liang, Spandon Garg, and Roshanak Salaukian Moghadam argues that performance gains on SWE-Bench Verified may be partially driven by memorization rather than genuine problem-solving. Their diagnostic is elegant. Models identify the buggy file path from the issue text alone with about 76% accuracy on benchmark repositories and only about 53% on repositories outside the benchmark. Public benchmarks built from public GitHub history are in the training data by construction. That is not fraud, it is arithmetic. The second is harness confounding, and it is the one engineers underrate. The same model scores very differently in different scaffolds, different tool definitions, different context management, different retry logic. Terminal Bench is honest about this. Its leaderboard reports agent and model pairs, not models. As of the 3rd of August 2026, the top entry on Terminal Bench version 2.1 was Claude Code with Fable 5 at 83.8%, plus or minus 1.2, with Codex and GPT 5.5 just behind at 83.1. Date those numbers, they will move. The point is not the ranking. It is that the benchmark concedes the harness is part of the system under test, whereas a model announcement usually does not tell you what scaffold produced the score. The third is distribution mismatch. SWE Bench is single repository, Python dominant, issued a patch, and comes with a ready-made oracle in the form of tests written by the people who fixed the bug. Your codebase is polyglot, has no oracle, and the issue is a message in Slack that says checkout is broken for some Canadian customers. The fourth is reporting effects and saturation. Vendors report their best configuration, sometimes best of many attempts, occasionally a filtered subset, and error bars rarely survive the trip to the marketing page. And benchmarks get saturated and replaced, the progression from SWE Bench to Verified to Pro, and Terminal Bench through its versions, is that treadmill. The rule I would put on a wall: public benchmarks tell you which models are worth trying. They tell you nothing about whether an agent will work on your codebase. Only your own evaluation does that. So what do you measure? 5 things, and they are all things your existing systems can already tell you. 1. Task success on your own work. A fixed set of tasks from your own backlog, scored by a script, that is the next chapter in full. 2. Review burden. Time from pull request open to first review, total review time, and how many reviewers a change consumes. This is where the cost hides. Pharaoh's AI, an engineering intelligence vendor, disclose the interest. They sell the analytics, published telemetry in April 2026, drawn from 22,000 developers and 4,000 teams, comparing each organization against its own lower adoption period. They report median time to first review up by more than 150%. Do not take the number as your number. Take it as a reason to instrument your own. 3. Defect escape rate. Defects reaching production per unit of change, split by whether the change was agent-assisted. That split requires you to record agent involvement in the commit trail, a trailer, or a label, which is a 5-minute policy decision that makes every future question answerable. Without it, you can never ask, which of our code was agent-authored, after you find a class of bug. 4. Rework. How much of what merged gets rewritten within the following weeks? Rework is where quality problems show up before incidents do. 5. Time to merge, plus cost per merged change in both tokens and wall clock. Speed to first draft is the metric vendors report. Speed to merged and operating is the metric you are paid for. Measure the throughput side and the stability side together, because the largest dataset in the field says they move in opposite directions. The 2025 DORA report, roughly 5,000 technology professionals, run by Google Cloud, which sells both AI coding tools and the platform products the report recommends as the fix, so state that interest before the finding, reports a positive relationship between AI adoption and delivery throughput and a negative relationship with delivery stability. Their framing is that AI is an amplifier. It does not fix a team, it magnifies what is already there. If you measure only throughput, you will conclude it is working, and the bill will arrive on the on-call rota. 2 honest gaps before we move on. There is no published longitudinal study of defect escape rates tied to AI authorship. There is no rigorous post-inflection, randomized trial replicating METR. Those absences are exactly why local measurement is not a nice-to-have. The literature cannot answer the question for you, and it will not by next quarter. One last piece of discipline. Take the baseline before you roll anything out, because after the rollout, the counterfactual is gone forever. A rollout without a before and after measurement plan does not produce data. It produces opinions held confidently. Which brings us to the practical work, building the evaluation set itself. 20 tasks from your own backlog and a decision you can defend. Chapter 9, Building Your Own Benchmark. This chapter is a build guide. By the end, you should be able to run a real procurement decision, which tool, which model, which configuration, on evidence from your own codebase, and defend it to someone who disagrees. It takes about 2 days to build the first time and a few hours to rerun. That estimate is my own from doing it, not a published figure. Start with the material because you already have it. Go to your closed tickets and pick roughly 20 that shipped, each with a known good diff attached, the change your team actually made and merged. Those diffs are your reference solutions, written by people who knew the system, reviewed by people who knew it too. You could not buy a better answer key. Select for representativeness, not difficulty. The instinct is to pick the interesting problems. Resist it. You are trying to predict how a tool performs on your work, so the set should look like your work. Sample the actual distribution, bug fixes, small features, a refactor, a dependency upgrade, a test coverage task, a config change, one thing in the ugly legacy corner nobody enjoys. Deliberately include 2 or 3 you expect the tool to fail. A set where everything passes measures nothing. It just tells you the ceiling is above your tasks. Then freeze the state and be strict about it. Each task is a repository pinned at the commit immediately before the real change landed, plus the ticket text exactly as it was written at the time, plus whatever linked context a human would have had. Do not clean up the ticket. Do not turn it into a well-structured prompt. If your tickets are terse and ambiguous, that is a property of your organization, and it is part of what you are measuring. A benchmark built from rewritten tickets tells you how the tool performs for a company you do not work at. Now pass criteria, which is where most homemade evaluations fall apart. The rule: prefer criteria a script can check and write them down before you run anything. Your default oracle is right there in the original change. Take the tests that shipped with it, run the pre-existing suite to catch regressions, and require the build and the linter to pass. Add a scope check. Did the diff touch files outside the set the real change touched, plus a reasonable margin? Scope creep is a real failure mode, and it is trivially scriptable. If the original change had no tests, write them once now. Yes, that is work. You are going to need that test anyway, and it converts a subjective task into a scriptable one permanently. Some tasks genuinely resist scripting, a refactor whose whole point was readability, a change whose value was in the error messages. Keep those, but keep them in a separate bucket, score them with a written rubric and a human, and label the 2 scores separately. Never blend a scripted pass rate and a human impression into one headline number. The moment you do, nobody can tell what moved. One caveat specific to this kind of set: if your repository is public, your tasks may be in the training data. Prefer private repositories. If you cannot, treat the results as an upper bound and say so. Now run it, and be precise about what a candidate is, because this is the mistake I see most often. You are not evaluating a model. You are evaluating a configuration. Model plus harness plus settings plus tool permissions plus your instruction files. The harness is part of the system under test, the public leaderboard that reports agent and model pairs rather than models alone is telling you exactly that. So hold everything fixed except the one variable you are changing. If you swap the model and the harness at the same time, you have learned nothing and spent the money anyway. Run every task at least 3 times per configuration because the system is not deterministic. Report the pass rate across runs. Do not report the best run. Best of many is what a vendor reports in an announcement, and it is not what your engineers will experience on a Tuesday. Record more than correctness. For each run, input and output tokens and the dollar cost, wall clock time, the number of times a human had to intervene or approve something, and the size of the resulting diff. This matters because the decision is rarely about correctness alone. A configuration that passes 18 of 20 at 4 times the cost and 3 times the wall clock is a completely different proposition from one that passes 16 cheaply and quickly. Without the cost and time columns, you cannot even have that argument, let alone win it. Now hold out discipline, which is the part people skip and the part that makes the whole thing trustworthy. Split your 20. Roughly 2/3 is your development set, the tasks you look at, debug against, and use while tuning your instruction file, your tool permissions, your hooks, your prompt templates. The remaining third is holdout. You do not look at it. You do not read its failures to get ideas. You run it only at decision points. The reason is not ceremony, it is a specific failure you will otherwise walk into. You will tune. Everyone does. You will notice the agent keeps missing your logging convention, so you will add a line to the instruction file, and the pass rate will go up. Do that a dozen times against your whole set, and you have not built a better configuration. You have fitted a configuration to 20 specific tasks. It is training on the test set, wearing a suit. The holdout is what tells you whether the improvement generalizes to the 21st ticket, which is the only ticket you actually care about. And a rule to state now while it costs nothing: if you ever debug against the holdout, it is burned. Retire it and cut new tasks from the backlog. That last part is your structural advantage over any public benchmark. Your backlog keeps producing fresh, uncontaminated, perfectly representative tasks forever for free. Now the trap I most want you to leave this chapter knowing about, because it is subtle and it will silently corrupt your results. A reviewer prompted to find problems will find problems. This is documented in Anthropic's own guidance for their coding tool, and I will give it to you in their words. A reviewer prompted to find gaps will usually report some, even when the work is sound, because that is what it was asked to do. They add the consequence. Chasing every finding leads to over-engineering, extra abstraction layers, defensive code, and tests for cases that cannot happen. Now apply that to evaluation. If you use a language model as your grader and ask it, what is wrong with this diff? It will tell you what is wrong with the diff, every time, for every candidate, including the reference diff your own senior engineer wrote and shipped last quarter. That grader is not measuring quality, it is measuring its own instruction following. 3 defenses. First, deterministic gates first, model second. Tests, build, lint, and scope checks decide pass or fail. A model may add commentary, but it does not hold the verdict. The pattern in the field is the same everywhere it works. Deterministic analysis first, model evaluation afterwards. Second, if you must use a model as a grader, give it a neutral rubric, score against these criteria, rather than find the problems. Use the identical prompt for every candidate, and never tell it which tool produced the diff. Blind your grader. Third, if the same model that wrote the code is grading it, run the grader in a fresh context that sees only the diff and the criteria, not the reasoning that produced the change, so it evaluates the result on its own terms rather than defending work it just did. Here is a cheap calibration trick that costs you one afternoon and buys enormous credibility. Run your reference diffs, the real changes your team shipped and merged, through your grading pipeline. If your pipeline flags your own shipped code as failing, your pipeline is broken, and you have found that out before you used it to reject a vendor. Finally, rerun discipline. This set is not a one-time exercise. It is an instrument, and instruments get recalibrated. Rerun when the model version changes, when the harness updates, when you add or remove a tool server, when you change permissions, and when you edit the instruction files. Model upgrades are not monotonic improvements. Armin Ronescher, an enthusiastic agent user rather than a skeptic, published a post in July 2026 titled Better Models, Worse Tools, subtitled as being about an aggravating tool calling regression in newer models. Better on paper, worse in the loop. Your set is how you find that out in an afternoon instead of a quarter. And verify what you actually ran. Some API endpoints that accept another vendor's model names will silently map an unrecognized name to a cheap default model rather than returning an error. One provider documents exactly that behavior. A typo does not fail loudly. It quietly invalidates every number you just collected. Log the model identifier the provider reports back, not the one you asked for. What you end up with is a table. For each candidate configuration, pass rate on the development set, pass rate on the holdout, cost per task, wall clock per task, interventions per task. That table is a procurement decision that survives contact with a vendor, a skeptical staff engineer, and your own enthusiasm 3 months later. And it converts every marketing claim into a testable proposition. When someone tells you their tool is better, you say, "On our 20, show me." Correctness is one axis of that table. The next chapter is about the column most teams get wrong first, what this actually costs, and why the bill behaves so strangely. Chapter 10, The Economics of Tokens. A token is the model's billing unit. Roughly a fragment of a word, call it 3 or 4 characters on average for English prose, fewer for dense code. You are charged separately for the tokens you send in and the tokens the model sends back. That is the entire pricing model. Everything else in this chapter falls out of one structural fact that nobody tells you on your first day. Here is the fact: the API is stateless. The model has no memory between calls. None. When you send the second turn of a conversation, you are not sending the second turn, you are sending the first turn, and the models reply to the first turn and then the second turn. All of it. Again. The third turn resends all of that, plus the second reply. Every single request carries the entire transcript from the beginning. If you have ever built against an endpoint with no session state, you already have the mental model. What is different here is that the request body grows monotonically, and you are billed by its size every time. Now add tools, because an agent is a model with tools. Every tool result is appended to that transcript. The agent reads a file, that file's contents are now in the conversation, and they will be resent on every subsequent turn until the session ends. It runs a test suite, and the suite fails noisily. That wall of output is now permanent freight. It greps a large repository and gets 400 matches back, all of it resent forever at your expense. And the tool definitions themselves are input tokens on every request. Not once at the start, every request. The JSON schemas describing what each tool does, what arguments it takes, when to use it. 20 connectors you never actually invoke still cost you tokens on every turn of every session. This is why Claude Code now defers loading MCP tool definitions by default and offers a search-based mechanism for large tool catalogs, rather than pasting the whole catalog into every request. There is also a hidden system prompt that the provider injects to enable tool use at all. Anthropic publishes the size of it per model. For Claude Opus 5 with automatic tool choice, it is 286 tokens. Small, but it is there, on every call, and it is the kind of thing that is invisible until you go looking for why your token counts do not add up. Put those two facts together, the whole transcript resent, and every tool result appended to it, and you get the property that matters. Cost does not grow linearly with the length of a session. It grows with roughly the square of it. Let me do the arithmetic out loud, because it is worth feeling. This is illustrative, not a measurement. Say a session runs 50 turns and finishes with 100,000 tokens of accumulated context. The context grew roughly steadily, so the average request over that session carried about 50,000 tokens of input. 50 turns times 50,000 tokens is 2.5 million input tokens billed, for one session, from one engineer. At $5 per million input tokens, that is about $12.50. Fine, but now notice what happens when you have the session. 25 turns finishing at 50,000 tokens averages 25,000 tokens per request. That is 625,000 tokens, a quarter of the cost, not half. Both the number of requests and the size of each request have together. This is the single most useful thing to internalize about agentic cost. Long sessions are not proportionally more expensive than short ones. They are quadratically more expensive. The engineer who runs 1 marathon session per day and the engineer who runs 4 scoped sessions per day may produce the same amount of work and receive very different bills. There is a mechanistic reason underneath this that Anthropic's own engineering writing states plainly. Transformers require, in their words, every token to attend to every other token across the entire context, producing n-squared pairwise relationships for n tokens. That is a statement about compute, not about billing directly. But the two point the same way, and it is why the answer to why not just paste the whole repository in is not simply the window is too small. Now, the second asymmetry. Output tokens cost 5 times input tokens. On every tier, from every frontier vendor I have prices for, that ratio is stable enough to treat as a rule. Agentic loops are output-heavy by construction. The model thinks that is output. It emits a tool call, output. It writes code, output. It gets a failing test and rewrites the code, output again. So the naive estimate an engineer reaches for, which is, how many tokens is my code base multiplied by the input price, understates agent cost badly. Teach yourself the asymmetry before you attempt any budgeting. Here are the actual numbers, and I want to frame them carefully. These are list prices for one vendor, Anthropic, read from a pricing reference cached in June 2026 and current as of August 2026. They are not a law of nature. They move, and one of them is about to. Verify before you budget against them. Claude Opus 5, $5 per million input tokens, $25 per million output. Claude Sonnet 5, $3 input, $15 output, with an introductory rate of $2 and $10 running through the 31st of August 2026, so that one is expiring within weeks of this recording. Claude Haiku 4.5, $1 input, $5 output, and Claude Fable 5 at the top, $10 input, $50 output. Note that Haiku input is 1/5 of Opus and 1/10 of Fable. Hold that ratio. It is the largest lever you have, and we will come back to it. Which brings us to the thing that makes agentic coding economically viable at all: prompt caching. Here is what it does. When the provider processes your request, it does expensive work turning your input tokens into internal state. Prompt caching lets you tell it to keep that state around for a short while, keyed on an exact prefix of your request. If your next request starts with the identical prefix, the provider reuses the cached state instead of recomputing it, and charges you accordingly. The economics. A cache read costs about 1/10 of the base input price. A cache write costs a premium, 1.25 times base for the 5-minute time to live, or double for the 1-hour one. So caching is not free, and it does not always pay. Break-even with the 5-minute window is 2 requests. 1.25 plus 1/10 is 1.35 against 2 full-price reads. With the 1-hour window, it is 3 requests. Beyond that, it is pure saving. Now look at what an agent session actually is. A large, stable prefix, system prompt, tool definitions, repository instructions, and every prior turn, followed by a small changing tail. That is very nearly the ideal shape for a prefix cache. Almost the entire resent transcript can be a cache read at 1/10 the price, with only the newest turn paid at full rate. Take my 50-turn example, $12.50 uncached, with effective caching on the order of 1/10 of that on the read side, plus the write premiums. Call it roughly 10 times cheaper. That is not a discount. That is the difference between a practice that a company can afford to roll out to 400 engineers and one it quietly cancels after the first invoice. And this is why I have put caching at the center of the economics rather than in a tips and tricks appendix. Everything else, routing to cheaper models, clearing context, batching, is a percentage. Caching is an order of magnitude. It is also the lever that most teams silently fail to pull, because caching depends on an exact prefix match, and when it breaks, nothing errors. Your code runs, your agent works. Your bill is 10 times what it should be, and there is no signal anywhere telling you so. That failure, and what to do about it, is where we go next. Chapter 11, Cost Control and Rate Limits. Prompt caching is worth an order of magnitude, and it fails silently, so we start there. Caching is a prefix match. Exact bytes from the first character of your request forward. The provider will reuse cached state for as long as your request is byte identical to the cached one, and the moment it diverges, everything from that point onward is recomputed and charged at full price. Any byte change anywhere in the prefix invalidates everything after it. Now think about what engineers routinely put at the top of a system prompt. A timestamp, today's date, helpfully injected so the model knows when it is. That single call to the current time changes the prefix on every request and destroys the cache for the whole session. A dictionary serialized without sorted keys, so field order varies run to run. A tool list assembled per user, in whatever order the map iterated. Each is a normal, sensible-looking line of code, and each means your cache never hits. And nothing tells you. There is no exception, no warning, no degraded response. The agent works exactly as well as it did before. You find out at the end of the month. The diagnostic is one field on the response. Anthropic's API returns a usage object carrying a cache-read input tokens count. Send the same prefix twice and look at the second response. If that number is 0, something is invalidating your cache and you have a bug to find. I would make this the first exercise on any team adopting these tools, ahead of anything to do with prompting. It is measurable, reproducible, and it maps directly to a real invoice. One nuance, because it bites people who go looking for cheaper inference. 3 different caching models exist in the wild and they are not interchangeable. Client-directed, where you place the breakpoints yourself. Server-automatic, where the provider decides, and accepted then discarded, where the endpoint takes your cache control field, returns 200, and ignores it. DeepSeek's Anthropic-compatible endpoint is documented as ignoring cache control, which does not mean no caching, because it caches automatically server-side. What you lose is control over breakpoint placement and the meaningfulness of your cache telemetry. Know which of the 3 you are in before you reason about cost. Second lever, and the largest one that requires no cleverness at all, model routing. Haiku input costs 1/5 of Opus and 1/10 of Fable. A great deal of what an agent does is mechanical. Finding where a symbol is defined, renaming things across a directory, summarizing a diff, extracting the failing assertion from 300 lines of test output. None of that needs the most capable model you can buy, and running it, there is simply setting money on fire. The harnesses support this directly. Claude Code's subagent definitions take a model field in their front matter, and the official documentation lists control costs by routing to cheaper models like Haiku as one of the stated benefits of subagents. So the mechanism exists, it is supported, and most teams do not use it. Route the mechanical work down a tier. Keep the expensive model for the parts where judgment actually matters. Third lever, clear the context between tasks. This one is free, it is one keystroke, and it fights the quadratic directly. Finish a bug fix, start an unrelated feature in the same session, and every token of that bug fix is resent on every turn of the feature work forever, for nothing. Claude Code's best practices documentation names this as a failure pattern, the kitchen sink session, and adds a sharper rule I have found reliably true. If you have corrected the agent more than twice on the same issue in one session, the context is cluttered with failed approaches. Clear it and restart with a better prompt. You are not being wasteful by throwing the session away. You are being wasteful by keeping it. Fourth, scope your investigations. The expensive thing in a coding agent is exploration. An agent hunting through an unfamiliar repository reads dozens of files, and everyone lands in the context and stays there. The structural fix is to explore in a separate context window that you throw away. A subagent runs with its own clean context, reads whatever it needs, and returns a condensed summary. Anthropic's engineering writing puts the typical size of such a summary at 1,000 to 2,000 tokens. 50,000 tokens of reading becomes 1,500 tokens of answer. The related discipline is just-in-time retrieval. Hold lightweight identifiers, file paths, queries, links, and load contents at the moment you need them rather than preloading everything you might. Fifth, Batch anything that does not need to be interactive. The Batch API is 50% off all token usage in exchange for accepting latency. A lintan fix pass over 400 files overnight, test scaffolds, a backlog classification. There is no reason to pay the interactive premium on any of it. One caution on the newest features. Agent teams, multiple full agent instances talking to each other, each with its own context window, are documented as using approximately 7 times more tokens than standard sessions when teammates run in plan mode, and are disabled by default for that reason. Every parallel context is a context you are paying for. Now the part where the money is actually decided, whether you are metered or on a seat. Coding agent subscriptions are priced per seat. The underlying inference is priced per token. Those are 2 different units, and a heavy user can consume far more inference value than the seat costs. Ed Zitron, writing in July 2026, puts the gap in the sharpest available form. You can, he says, burn $14,000 in tokens on a $200 a month subscription. Name the incentive. Zitron is a professional critic of this industry whose newsletter and podcast audience is built on the thesis that it is a bubble. He is as motivated toward the bearish read as any vendor is toward the bullish one. But that particular figure is checkable arithmetic rather than a forecast, and the structural point stands regardless of what you think of his conclusions. 3 things follow for an engineering organization, and none of them require you to accept the bubble thesis. Subscription pricing is a promise, not a cost floor. If your capacity plan assumes seats, you have taken an unhedged position on somebody else's pricing decision. Rate limits are the mechanism by which that promise gets enforced. When metered value exceeds seat price, the vendor's lever is not usually a price rise, it is a usage cap. The weekly and rolling caps you see on subscription coding tools are that mechanism made visible. And metered pricing, though more expensive, is more honest, because spend is observable and attributable per task, which is the only basis on which real capacity planning is possible. So here is the hedge, and it is cheap. Measure your real token consumption per task through metered pricing at least once, even if you buy seats. Then you know what your workflow costs if the subscription arrangement changes tomorrow. Which brings us to the question everyone asks, what does this actually cost per developer? The research has 3 grounded figures, and they disagree wildly. The honest move is not to pick one. It is to notice that they are measuring 3 different things. Jeffrey Huntley, writing in February 2026, states that the cost of software development is $10.42 an hour, which is less than minimum wage. That is token spend per agent hour. It is his own arithmetic, not an audited figure, and he is a prominent advocate of brute force autonomous agent loops, so name that. It excludes review time, rework, incident cost, and the salary of the human deciding what to build and whether it is correct. Treat it as the floor, the marginal cost of generation, measured honestly. Second, Gergely Oros, reporting in The Pragmatic Engineer in July 2026 on Bun's rewrite into Rust, gives a figure of $165,000 in tokens over 11 days, for work characterized as something that would have taken a small team a year. That is a fully loaded project figure, and it is favorable on any plausible assumption. But it is a migration. A source of truth already exists and correctness is checkable against the original, performed by an elite team on their own codebase and reported by the people who did it. That is the best case shape of task for an agent. Do not generalize it to greenfield product work. And note that most of that article sits behind a paywall. The numbers come from the accessible portion. Third, Steve Yegg forecasts token budgets of $50,000 to $100,000 per developer per year. That is a prediction about what organizations will need to budget, not a measurement of anything. He was at SourceGraph, which sold an agent product, when he wrote it. Say that out loud. $10 an hour, $165,000 for one project, $50,000 a year per head. Those are a floor, a case study, and a forecast. They do not contradict each other. Anyone quoting one of them at you as the answer has picked the one that suits their argument. The last thing to internalize is that spend is not proportional to task size. An agent that retries, rereads the same files, or gets stuck in a loop burns tokens with nothing to show for it. Cost is a function of convergence, not of diff size, which is why estimating from lines of code is systematically wrong, and why your bill will be lumpy in ways your ticket sizes do not predict. Budget for variance, alert on it, and treat an unexplained spike as what it usually is. An agent that could not converge on something, silently, for an hour. All of that assumes today's prices hold. The next chapter asks whether they will. Chapter 12, is any of this priced honestly? Every cost calculation in the last 2 chapters rests on a price. So the obvious next question is whether that price is real, whether you are paying what it costs to serve you, or whether you are paying a number chosen to acquire you, underwritten by investors who expect to be repaid later out of a much larger business. I want to be straight about how this chapter ends before we start it. I cannot answer that question, and neither can anyone outside these companies. Not because the topic is complicated, and not because I have not looked. Because the one number that would settle it is not published by anybody. Neither Anthropic nor OpenAI discloses the cost of goods sold on inference. There is no public figure for what it costs to serve 1 million tokens. Every public claim that inference is sold below cost, every one, including the strongest, is an inference drawn from capital expenditure and revenue figures, not a reading of disclosed unit economics. That is a materially weaker kind of evidence, and pretending otherwise would teach you a bad epistemic habit at exactly the moment you need a good one. So instead of an answer, here are both cases at their strongest, and then something you can actually do that does not depend on which is right. The case that current pricing is a subsidy is made most forcefully by Ed Zitron, writing in July 2026. Name his incentive first, as we do with everyone. Zitron is a professional critic of this industry and a public relations firm chief executive whose newsletter and podcast audience is built on the thesis that this is a bubble. He is as motivated toward the bearish read as any vendor is toward the bullish one. That does not refute his figures, most of them are other people's, but it is the standard this course holds everyone to. His argument runs on scale. Citing reporting by The Information, he puts OpenAI on course to burn over $852 billion by the end of 2030, with $748 billion of remaining performance obligations across Microsoft, Amazon, and Oracle, and over $50 billion on compute in 2026 alone. On Anthropic, he cites $200 billion of compute and hardware commitments to Google, and $35 billion raised in debt from Apollo to buy Google's tensor processing units. Citing Goldman Sachs, he puts combined hyperscaler capital expenditure at $765 billion in 2026. Then he lands the arithmetic that matters most to you. Quote, you can burn $14,000 in tokens on a $200 a month subscription. And on the revenue side, he notes that OpenAI is expected to make $2.4 billion in advertising revenue in 2026, rising to $102 billion by 2030, against eMarketer's projection that the entire artificial intelligence chatbot advertising industry, combined, makes about $1 billion in 2026. Treat those individual dollar figures as medium confidence. They are his reporting of third-party reporting. Now the other side, stated as strongly as I can make it, and I will flag which parts are documented and which are my own reasoning. Documented, prices have fallen repeatedly across every vendor and every tier for years. Documented, the discount structures themselves are aggressive and durable. A cache read costs about 1/10 of base input price. The batch endpoint is 50% off. Haiku input is 1/5 of Opus. Those are not one-off promotions. They are standing structural features of the pricing model. Here is my inference, and I want it labeled as inference rather than a documented finding. You do not typically build a permanent 90% discount into your product for the highest volume path through it if that path is already underwater. Prefix cache reads are the dominant cost in agentic workloads, and they are the cheapest thing on the menu. That is more consistent with a provider that has serving cost headroom on cached prefixes than with one bleeding on every token. Second, and this one is straightforward logic rather than opinion, capital expenditure is not the same line as marginal serving cost. Building data centers, buying accelerators, and training frontier models are enormous fixed and forward-looking costs. The cost of serving one more token to one more customer on hardware you already own is a different number entirely. A company can be losing spectacular amounts of money in aggregate while its marginal inference is comfortably profitable. Both things can be true simultaneously, and citing the capital expenditure figure does not settle the serving cost question. It is evidence about the balance sheet, not about the unit. Third, and this one cuts directly at the most quoted figure in the debate, burning $14,000 of tokens does not mean the vendor spent $14,000. That is $14,000 at list price. List price and cost are related by a margin nobody has published. The arbitrage arithmetic proves that seat pricing and metered pricing have diverged, which is a genuinely important, genuinely actionable fact, and I built a recommendation on it in the last chapter. It does not prove the metered price is below cost. Those are different claims, and they get conflated constantly. So, two coherent stories, both partly evidenced, neither decidable. Baldur Bjarnason, writing in March 2026 about a different argument entirely, why optimists and skeptics observing the same tools reach opposite conclusions, made an observation that I think generalizes here. His line is that there is nothing either group can say to the other to shift their opinion, because the disagreement comes down to a fundamental difference in worldview. He was writing about productivity, not pricing, and I am extending his point rather than reporting it. But the shape is the same. When the decisive evidence is unavailable, what looks like an argument about numbers is an argument about priors, and it does not resolve. Which is why I am not going to give you a verdict. I am going to give you a posture. Plan as though pricing is a variable you do not control, because it is. Not because I predict a repricing, but because you have no basis on which to predict its absence, and that asymmetry is what engineering judgment is for. You would not architect a system around a third-party API whose pricing and availability you had no visibility into and no contract on, and then treat its permanence as a load-bearing assumption. Do not do it here either. The concrete form of that posture is portability. Build so that a price change or a provider change is survivable. In practice, that means a few specific things. Keep the harness and the model separable and know which of your workflows depend on which. Keep your repository instructions, your Claude.md, your agents.md, as plain files in version control, because they are the accumulated knowledge of how agents should behave in your codebase, and they should not live inside a vendor's account. Keep the evaluation set we built earlier in this course, the 20 tasks from your own backlog, because that is the only instrument you have for judging whether a replacement is actually adequate. And measure your real cost per task, so that when you have to price a switch, you are comparing two measurements instead of two hunches. Now the honest part, because portability sold as a checkbox is a lie, and the research is clear on this. Pointing a coding harness at a different vendor's model is not a supported configuration. Anthropic's own gateway documentation states plainly that Anthropic does not support routing Claude code to non-Claude models through any gateway. So this is an explicitly unsupported path, not merely an undocumented one. Teach it as a real and popular practice with real caveats, never as a supported one. And there are 3 verified ways it goes wrong, all of which produce the same user-visible symptom: the model seems dumber, while the actual fault is in the plumbing. First, context window misdetection. Claude code falls back to a hard-coded 200,000 token default for third-party endpoints, so a provider genuinely serving 1 million tokens of context triggers automatic compaction at roughly 19% of real capacity. The user experiences an agent that keeps forgetting what it was doing and blames the model. Second, translation layer corruption. In one open-source router, a reasoning transformer corrupted tool call arguments badly enough that a measured 10 out of 10 valid tool calls with the transformer disabled became 0 out of 10 with it enabled, same model, same prompts. Third, silent downgrade. DeepSeek's Anthropic-compatible endpoint maps Claude model names onto its own and silently defaults any unmapped model string to the cheap model rather than returning an error. A typo does not fail loudly. It quietly downgrades you, which invalidates any benchmark you thought you were running. Add one more, because it connects to the structural fact this whole section is built on. Once a single malformed tool call enters the conversation history, subsequent calls tend to imitate it, because the history is resent every turn and the error has become a worked example the model is copying. That failure is absorbing, not transient. Retraining does not fix it. Truncating the history does. So portability is not a switch you flip in an emergency. It is a capability you maintain and periodically test, the same way you treat a disaster recovery plan you have never rehearsed, which is to say, as something you should assume does not work until you have proven it does. That is the honest ending. The sustainability question does not resolve, and building as though it might not go your way costs very little and hedges an outcome you cannot forecast. Money is only half of the long-run cost, though. The other half is what happens to the codebase itself. That is next, and the evidence there is even messier. Chapter 13. What happens to a codebase over time? Part 1 of this course set a rule when we looked at the context-drought research. State the interest, then the number, in that order, every time. Nowhere does it matter more than here, because on this question, almost every figure in circulation was published by a company that sells a remedy for the problem it is measuring. So before any number, the ledger. This is the frame for everything that follows. METR, the nonprofit evaluations organization whose randomized trial found experienced developers 19% slower while believing they were 20% faster, sells nothing. No product, no remediation, no dog in the fight. It is the cleanest measurement in the corpus, and that is the exception rather than the rule. DORA, the research program run by Google Cloud, sells the thing directly. Google Cloud sells AI developer tooling, and it also sells the platform, testing, and continuous integration products that the DORA report prescribes as the fix. GitClear sells the instrument. GitClear's product is code quality and diff analytics. It measures a decline in code quality, and it sells the tool for detecting that decline. Its founder, Bill Harding, is also the report's author. Pharaoh's AI sells engineering intelligence software, dashboards over exactly the delivery metrics its report says are deteriorating. Apiero, an application security vendor. It reports a surge in security findings, and it sells the product that finds them. Stack Overflow, partly conflicted. No remediation product for code quality, but its core question and answer business is directly disrupted by these tools, and it now sells AI products of its own. The Stanford Digital Economy Lab on employment effects, academic working from third-party payroll records, clean. And vendor engineering blogs, Anthropic's included, entirely conflicted. Cite them for definitions and mechanism, never for effect sizes. None of that means the conflicted sources are wrong. GitClear may be measuring something real precisely because it built the instrument to see it. Google Cloud has the largest dataset in the field. The rule is disclosure, not dismissal. Start with Dora because it is the biggest sample. The 2025 State of AI-Assisted Software Development Report, published on the 24th of September 2025, roughly 5,000 technology professionals worldwide. 90% use AI at work. More than 80% believe it has increased their productivity. Pair that with METR every single time you hear it, because METR measured a 39-point gap between what developers believed and what happened. 30% report little or no trust in AI-generated code. Now the finding that matters. DORA reports a positive relationship between AI adoption and delivery throughput and with product performance. That was a change from the previous year, and a negative relationship with software delivery stability. That part was unchanged. Their own framing, verbatim. AI accelerates software development, but that acceleration can expose weaknesses downstream. Without robust control systems, like strong automated testing, mature version control practices, and fast feedback loops, an increase in change volume leads to instability. That converts a vague worry into a testable proposition. Change volume goes up. If the control system does not go up with it, stability goes down. That is measurable in your own organization this quarter. Note that DORA's headline conclusion, that AI is an amplifier, magnifying an organization's existing strengths and weaknesses, is commercially convenient. It converts a question about model capability into a question about platform maturity, and Google Cloud sells platform maturity. That does not make it false. And the throughput up, stability down split cuts against a pure sales narrative, which is a point in its favor. Say both things. Now get clear, and I am going to be careful here in a way that matters. The interest first, Get Clear sells code quality diff analytics, and its founder wrote the report. Then a second disclosure, about my evidence rather than theirs. The most recent research pass behind this course tried twice to fetch Get Clear's research pages, and both attempts returned an HTTP 403. The figures I am about to give you were recorded in an earlier pass against secondary coverage, and I have not re-verified them against Get Clear's own pages. I am telling you that rather than pretending otherwise. Treat them as a direction of travel, not a magnitude. The 2026 report, titled The Maintainability Gap, produced by Get Clear with Git Kraken, analyzed roughly 623 million real-world code changes between 2023 and 2026 across 8 quality signals. Duplicated code blocks up 81%. Refactoring, what Get Clear calls move operations, code being relocated and reused rather than copied, down 70%. Long-term legacy maintenance activity down 74% against a 2022 baseline. Error masking constructs, meaning broad catch blocks and silently swallowed exceptions, up 47%. 2-week churn, code revised within a fortnight of being committed, up 15%. Harding's own nuance, and he deserves credit for stating it. Some signals are flattening. He says it is encouraging that duplication did not increase as much and churn only somewhat. His larger concern is the neglect of long-term legacy maintenance, not duplication alone. Now the methodological honesty. These are correlational trends over calendar time, not a controlled comparison of AI-authored against human-authored code. A great deal changed in the industry between 2020 and 2026 besides AI adoption. Get Clear's classification of moved versus copy-pasted code is proprietary. You cannot audit it. And moved code declining is a proxy for refactoring declining. Reasonable, but a proxy the vendor chose. For a decline the vendor sells the detector for. Duplication rising is more direct and travels better. Then there is Pharaoh's AI, and this is where it gets genuinely interesting, because Pharaoh's contradicts DORA head-on. The interest first, Pharaoh's sells engineering intelligence software. Their report, published on the 12th of April 2026 under the title The AI Acceleration Whiplash, covers 22,000 developers across more than 4,000 teams over 2 years of continuous enterprise telemetry. Its design is better than most. It compares each organization against itself, its lowest AI adoption period versus its highest, rather than comparing different companies to each other. And it is not a survey. It is measured from version control, continuous integration systems, and incident trackers. The throughput side agrees with DORA. Epics completed per developer up 66%, task throughput per developer up roughly 34%, pull request merge rate per developer up roughly 16%. The quality side is ugly. Code churn up 861%. The ratio of incidents to pull requests up roughly 240%, production incidents roughly tripling per unit of change shipped, monthly production incidents up roughly 58%, and bugs per developer up 54%, which in Pharaoh's own prior year edition had been up only 9%. Their reading is that the quality gap is widening as adoption deepens, not closing. Here is the collision. Pharaoh's reports that high-performing engineering organizations experience the same downstream deterioration as everyone else. Strong foundations did not protect them. That is a direct contradiction of DORA's central thesis that AI amplifies existing capability and that strong teams get better outcomes. I am not going to resolve that for you because it is not resolved. There is a plausible reconciliation, labeled as speculation. DORA measures self-reported team capability against delivery outcomes at a point in time, while Pharaoh's measures the same organizations before and after, and even an excellent organization has a fixed review capacity that agents can saturate. That is a hypothesis, not a finding. What you have is two large data sets, both from commercially interested parties, pointing in incompatible directions. And Pharaoh's caveats are real. Vendor report, no peer review, no published confidence intervals. Comparing highest adoption to lowest adoption periods conflates AI adoption with calendar time and with everything else that changed in those organizations. And some figures, churn up 861%, are extreme enough that I would want to see the metric definition before I believe the magnitude. Now the part that a certification course gains more credibility from than any statistic. What is missing? There is no published longitudinal study of defect escape rate tied to AI-assisted authorship. As of August 2026, there is no high-quality randomized controlled trial that randomizes AI usage and then measures defect rates in production over time. That study does not exist. The question everyone actually cares about, does this code break more often once it is live, has not been answered to any standard you would accept in another engineering context. There is no review burden time study. The Stack Overflow figures are the closest available, and they are self-report. There is no post-inflection replication of METR. And there is no measurement at all of what Armin Ronasher describes when he argues that agents erode a team's shared understanding of its own system. That claim is argued, not measured, and he would tell you so himself. So the honest summary is this: throughput up on 2 independent datasets, stability down on 2 independent datasets, trust down, experienced developer speed unclear to negative on the one clean randomized trial we have, which predates the capability step change, maintainability contested and undermeasured. And the best-known maintainability dataset in the field comes from a vendor that sells the measuring instrument. This is the weakest evidenced important question in agentic coding, and I would rather tell you that than hand you a confident number. Which leaves you one option, and it is the right one anyway: measure your own. You have the diff history, the incident log, and the review timestamps for your codebase. Nobody else does. Pick 4 signals: duplication, 2-week churn, review latency, incidents per pull request, baseline them before you scale adoption, and watch them. That is a better instrument for your decisions than any vendor report, and it is the only one nobody is selling you. One of those 4 signals is about to become the whole story. Review latency is where the throughput gains go to die, and that is the next chapter. Chapter 14, the review bottleneck. You already know the theory of constraints. A system's throughput is governed by exactly one resource at a time. Improving anything that is not the constraint does not increase throughput. It increases work in progress in front of the constraint, and work in progress is not value, it is inventory. Now apply it honestly to what you have just done to your own team. For most of this profession's history, the constraint on shipping software was producing correct code. Not the only cost, but the binding one. Coding agents attack that constraint directly, and since the capability step change, both Andrej Karpathy and Simon Willison independently date to late 2025, they attack it effectively. Willison's framing of the consequence is the cleanest available. Writing code is cheap now, and the scarce resources are review, verification, and judgment. So the constraint moved. It did not disappear. It is now sitting on the desk of whoever reads the diff, and that person is exactly as fast as they were last year. Here is what that looks like in telemetry. Farrow's AI, in their April 2026 report, and name the interest, they sell engineering intelligence dashboards over precisely these metrics, measured 22,000 developers across more than 4,000 teams, comparing each organization's lowest AI adoption period against its highest. Median time to first review, up roughly 157%. Average review time, up roughly 200%. Median review time, up roughly 440%, call it 5 times. Daily pull request context per developer, meaning the number of separate changes a reviewer has to hold in their head in a day, up roughly 67%. 26% more in-progress tasks, sitting with no activity for a week or more. Work restarts up roughly 14%. Queue time up, queue length up, work in progress up. Context switching up. That is not a list of unrelated problems. That is the textbook signature of a constraint being saturated, and it is what the theory predicts should happen when you elevate a non-constraint. And then the number that should make you sit up. Pull requests merged without review, up roughly 31%. That is the system routing around its own quality gate. Not by decision, not by policy change, by pressure. When the queue in front of a constraint grows faster than the constraint can drain it, and there is a path around the constraint, traffic takes the path. Everyone who has run an on-call rota knows this shape. There is a second mechanism making each unit of review harder, not just more numerous. A PIRO, an application security vendor, so selling the fix for what they are reporting, observed across tens of thousands of repositories at Fortune 50 enterprises that a AI-assisted pull requests pack more change into fewer, larger pull requests, touching more of the codebase. Larger diffs, spanning more files, arriving faster. Reviewability degrades superlinearly with diff size. Every reviewer knows a 400-line diff gets a fraction of the scrutiny per line that a 40-line diff gets. Their composition finding is the one I would put on a wall. Under AI assistance, syntax errors fell about 76%, and logic bugs fell about 60%. The shallow stuff genuinely got better. Meanwhile, privilege escalation paths rose over 300%, and architectural design flaws rose over 150%. Their researcher Ida Nussbaum's summary: AI is fixing the typos, but creating the time bombs. 2 honest caveats. Jeff Williams, co-founder and chief technology officer of Contrast Security, a competing security vendor, so name that too, publicly disputes a PIRO's numbers, arguing other studies show much lower figures. 2 security vendors disagreeing about a security statistic is exactly the epistemic situation to expect here. And mechanically, more code produces more findings. If code volume rose 3 to 4 times and findings rose 10 times, that is roughly 2.5 to 3 times per unit of code, not 10. But the direction survives the argument, and the direction is the point. The errors that got cheaper to find are the ones a reviewer catches in seconds. The errors that got more common are the ones that require holding the whole system in your head. Which brings us to why reviewing is harder than writing, and I want to make this argument properly, because it is usually asserted rather than explained. When you write code, the artifact is a byproduct. The real output is the model you built in your head while working, the constraints, the alternatives you rejected, the reason this function takes that argument. The code is a serialization of that model. When you review, you get the serialization and none of the model, and must reconstruct it from the artifact alone. That was always true of human code review, and always partly mitigated by the author being a colleague who shared your architectural assumptions and could be asked. With an agent, there is no model to share. Birgitta Berkler of ThoughtWorks put the categorical version of this better than anyone. Large language models are not compilers, interpreters, transpilers, or assemblers of natural language. They are inferers. You do not review a compiler's output, because its behavior is the language specification's responsibility. An inferer's output is a probabilistic draft, and its behavior is yours. And the failure mode shifted. Stack Overflow's 2025 developer survey, partly conflicted, since Stack Overflow's core business is disrupted by these tools, and it now sells AI products of its own, found 66% of developers naming, as their top frustration, AI solutions that are almost right but not quite. 45% said debugging AI-generated code takes longer than writing it manually. Obviously wrong code is cheap. It fails immediately and loudly. Plausibly wrong code is expensive because it passes review. Armin Ronusher, a heavy agent user, not a skeptic, which is what makes his warning land, describes the organizational version. Large software projects, he writes, have never been limited only by how quickly an individual can produce code. They are limited by how well people can coordinate their understanding. Agents remove that friction. And his conclusion from July 2026, the tower does not fall, and so we do not notice what was lost. It just keeps rising. Reviewing against an architecture nobody holds in their head is not review, it is proofreading. So, 4 responses, in descending order of how much I trust them. First, and by far the most important, small diff discipline. This is the only lever that reduces load at the constraint rather than adding capacity to it. Constrain the unit of work before it is generated, not after it arrives. Scope each agent task to something you would have scoped a pull request to and refuse to accept a larger one. Everything else on this list is capacity. This is demand management, and demand management is what the theory of constraints actually recommends. Second, agent-assisted first-pass review with a fresh context. Claude Code's own documentation names this the writer-reviewer pattern and gives the reason directly. A fresh context reviews better because it is not biased toward code it just wrote. That is a real property, not a marketing claim. The reviewing context has no memory of the reasoning that produced the code, so it cannot be persuaded by it. Run it as a separate subagent with its own clean context window. Third, require evidence, not assertions. The documentation puts the problem crisply. The agent stops when the work looks done, and without a check it can run, looks done is the only signal available, and you become the verification loop. So make it produce artifacts. Test output, a command exit code, a diff against a fixture. There is an escalation ladder here, weakest to strongest, an instruction in the prompt. A session-level goal condition rechecked each turn, a stop hook which deterministically blocks the turn from ending, a separate verification subagent rechecking with a fresh model. Note the distinction that makes the latter meaningful. Repository instruction files are advisory, hooks are deterministic and guarantee the action happens. If it matters, do not write it down and hope. Enforce it. Fourth, tests as the guardrail. Willison's red-green test-driven development pattern arrives at this from practice. DORA's prescription of strong automated testing arrives at it from a 5,000-person survey. 2 independent sources converging on the same lever is about as good as this field's evidence gets. Now the caveats, because I would be selling you something otherwise. A reviewer prompted to find gaps will usually report some, even when the work is sound, because that is what it was asked to do. That is stated plainly in Anthropic's own guidance, and it is the single most important thing to know about agent-assisted review. If you chase every finding an adversarial reviewer produces, you will over-engineer, and you will have converted a review bottleneck into a rework bottleneck. Triage the findings, do not obey them. And the bigger honesty. As of August 2026, no study has been found measuring whether AI code review reduces production defects. None. The most popular proposed fix for the bottleneck AI created is itself unevaluated. Use it, I do, but hold it as a practice you believe in, not a result you can cite. The last thing to notice is who all this lands on. Reviewers are senior engineers. There is a documented failure mode where, after the 10th approval prompt in a session, you are not really reviewing anymore, you are just clicking through, and that applies to diffs at least as much as to permission dialogues. The constraint is not just saturated. It is being asked to work in exactly the conditions under which human attention is known to fail. Which raises the question the next chapter has to answer. If the constraint is senior review capacity, and senior engineers are made by doing the work agents now do, where does the next generation of reviewers come from? Chapter 15, Skill Atrophy and the Junior's Problem. Two worries travel under one name, and they get muddled constantly. I want to keep them apart because the evidence behind them is different, and so are the answers. The first is personal. If you delegate the writing, do you erode the capability you need in order to supervise the writing well? That is a question about you, and you can act on it tomorrow morning. The second is structural. Agents now do a great deal of the work junior engineers used to learn on. If the bottom rungs come off the ladder, where do senior engineers come from in 10 years? That is a question about the profession, and no amount of personal discipline solves it. Take the personal one first and begin with an absence. There is no longitudinal study of engineer skill atrophy under agent use. Nobody has followed a cohort of working engineers for 3 years, measured what they could do at the start, and measured it again at the end. That study does not exist. On the central question of this chapter, the direct evidence is nil, and I am not going to dress up plausible reasoning as a finding. What we have instead is adjacent evidence, and it is worth being precise about what each piece does and does not show. The first piece is about self-assessment rather than skill. In the randomized trial run by METR, published in July 2025, 16 experienced open-source developers worked on 246 real issues in their own mature repositories. They were measurably 19% slower with AI assistance, and afterwards they still believed they had been about 20% faster. That is roughly a 40-point error in self-assessment from experienced engineers on code they knew intimately. METR has since said its follow-up design broke down and that the 19% figure should not be read as a present-tense fact. But the perception gap has not been retracted, and it is the finding that matters here. If your skill were quietly degrading, the instrument you would use to notice, your own sense of how well things are going, is the exact instrument that study showed to be unreliable. The second piece is from a controlled study at Stanford, published at the CM Computer and Communications Security Conference in 2023. Participants with an AI assistant wrote significantly less secure code than those without, and were more likely to believe their code was secure. But there is a third finding almost nobody quotes, and it is the useful one. Participants who trusted the AI less and engaged more with the language and format of their prompts produced code with fewer security vulnerabilities. Engagement was protective. That is a snapshot on old tooling, not a longitudinal result. It still points somewhere. The third piece cuts the other way from what people expect. Adi Osmani, an engineering leader on Google Chrome, wrote in December 2024 that these tools help experienced developers more than beginners, because, in his words, the more you know, the better you can guide them. Note the date. That is a pre-agent essay, and the ratios in it have plainly moved. The shape of the argument has not been refuted. The magnitudes should not be quoted as current. And the fourth piece contradicts the third, or appears to. The largest randomized sample in the field, 3 field experiments at Microsoft, Accenture, and an unnamed Fortune 100 manufacturer, 4,867 developers, published in Management Science, and therefore genuinely peer-reviewed, found that less experienced developers adopted more and gained more, and senior developers gained least. Both can be true, and I think they are, because they measure different things. The management science work counts completed pull requests. Osmani is talking about getting all the way to a correct, maintainable system. Someone with less context gains throughput. Someone with more context gains certainty that the throughput was pointed in the right direction. So resist both reflexes. Everyone is going to get stupid is an empirical claim with no data behind it. It will be fine is also an empirical claim with no data behind it. What we can reason about is mechanism, and the mechanism is unremarkable. Capabilities you stop exercising decay, and capabilities you exercise more sharpen. The interesting question is which capabilities move in which direction. Karpathy put the distinction better than I can, writing in April 2026. You can outsource your thinking, but you cannot outsource your understanding. Delegating the typing does not automatically cost you anything. Delegating the understanding does, and the loss is silent, because nothing fails on the day it happens. Now the practices, because this chapter should leave you with something you can do. The best documented mitigation comes from Mitchell Hashimoto, co-founder of HashiCorp and now the author of the Ghosty Terminal Emulator, writing in February 2026. He delegates routine work to agents and, in parallel, deliberately keeps doing deep manual work on the parts he cares about. His own words, he would work on something else in his own normal, pre-AI deep thinking mode. He names the skill formation risk of delegating routine work explicitly, and his answer is behavioral rather than technological. It generalizes: reserve a category of work that you do by hand, name it out loud, and defend it against your own convenience. Not, I will sometimes code manually, which decays to never within a month. A named category, the parts of the system you own architecturally, production debugging. The first implementation of any pattern you have not used before. Second practice, change what done means for you. Kent Beck, writing in June 2025, drew the line as a value system rather than a technique. In vibe coding, you do not care about the code, only the behavior of the system. In augmented coding, you care about the code, its complexity, the tests, and their coverage. Same value system as hand coding, different division of labor. If your standard is unchanged, the skills that standard requires stay in use. Third, read diffs properly and explain changes out loud. Simon Willison's test for whether you have merely vibe coded something is whether you reviewed it, tested it, and can explain it to someone else. That test is also a training exercise. Explaining a change you did not type forces you to reconstruct the reasoning, which is precisely the muscle at risk. Fourth, use instruments, not impressions. Since self-assessment is measurably miscalibrated, the honest check on your own skill is external. Do a task cold, occasionally with no assistance, and notice how it goes. That is not nostalgia, it is calibration. Now the structural problem, which is where the strongest evidence in this entire course sits. In November 2025, Eric Brynjolfsson, Burrit Shandar, and Ruyu Chen of the Stanford Digital Economy Lab published a study called Canaries in the Coal Mine. It uses high-frequency administrative payroll records from the largest payroll software provider in the United States. Millions of workers, not a survey, not self-report. The headline finding is a 16% relative decline in employment for early career workers, ages 22 to 25, in AI-exposed occupations, while employment held steady or grew for less exposed occupations and for experienced workers in the same roles. In their words, employment declines are concentrated in occupations where AI is more likely to automate rather than augment human labor. And the adjustment happens primarily through employment rather than compensation. Jobs, not wages. State the incentives, as this course does every time. The Stanford Digital Economy Lab sells nothing that fixes this. It is academic work on third-party payroll data and one of the cleanest sources in the corpus. The caveats belong in the same breath. This is a relative decline against less exposed occupations, not necessarily an absolute collapse. Good controls are not proof of causation, and the period overlaps a broad technology sector contraction which the authors attempt to control for. Present it as the strongest available evidence, not as proof. Here is the part no dataset can settle. Senior engineers are the people who can supervise agents. Senior engineers are made by doing the work that agents now do. If the apprenticeship path narrows, the supply of people qualified to review agent output shrinks at exactly the moment the volume of agent output grows. That is not a prediction I can verify. It is a structural argument, and I am labeling it as my inference rather than a documented finding. The honest counter deserves airtime, and it comes from Steve Yegg in an essay called Revenge of the Junior Developer. His argument is that agents invert the seniority advantage. Juniors, being less invested in the identity of typing code, adopt faster and win. His line is that it is not AI's job to prove it is better than you, it is your job to get better using AI. Disclose the incentive, as always. At the time of writing, he worked at SourceGraph, which sold an agent product. And note that his timeline predictions, engineers supervising fleets of 100 agents by early 2026, are now checkable. Fleet of 100 supervision is not median practice. Multi-agent parallelism plainly is. Score it as directionally early rather than wrong. Both things can be true. Juniors may adopt faster and still be hired less. Adoption speed is about individuals, the payroll data is about demand. If you run a team, 3 cheap things follow. Make code review a training assignment rather than a chore, because reviewing agent output is the skill the next decade actually needs. Use the agent as an explainer for juniors. Walking a codebase in execution order is one of the strongest documented uses of these tools. And give new engineers the failure modes deliberately, as labs, so that they have seen an agent fail in a known way before they have to catch one failing in an unknown one. Which brings us to the thing that does not change no matter who or what produced the diff. Your name is on the commit. Chapter 16, Accountability for Code Nobody Wrote. Here is the sentence I would put at the top of any team's AI coding policy, and I would make people read it before they get access to anything. The human who merges owns the code, unconditionally. That sentence exists to foreclose a defense before anyone tries it. The defense is the tool generated it, and it will be attempted in a post-incident review by someone under pressure, and it must not work. Everything else here is an elaboration of that one line. Start with why that defense is wrong on the technical merits, not merely unattractive. Birgitta Berkler, a distinguished engineer at ThoughtWorks and its global lead for AI-assisted software delivery, wrote the cleanest one-line correction available in a field memo dated July 2025. Large language models are not compilers, interpreters, transpilers, or assemblers of natural language. They are inferers. Sit with the difference because it does all the work. When a compiler emits machine code, you do not own that machine code line by line, and nobody expects you to. The compiler is deterministic, and its behavior is the language specification's responsibility. Miscompile correct source, and that is a compiler bug, with a vendor and a standard to appeal to. An inferer offers none of that. Its output is a probabilistic draft. Run the same prompt twice, and you may get 2 different plausible programs. There is no specification the output conforms to, no obligation that it be correct, no bug report that makes it your supplier's problem. So the accountability question, which sounds philosophically fraught, has a boring and complete answer. The same one as before. You own what you ship. Simon Willison drew the line in March 2025, and his definition is the policy. Vibe coding, in his narrow sense, is building software with a large language model without reviewing the code it writes. Not using a model, not letting it write most of it. Specifically, not reviewing. His test is that if you reviewed it, tested it, and can explain it to someone else, what you did was responsible software development. Kent Beck, writing in June 2025, gives the same line from the values side. In vibe coding, you do not care about the code, only the behavior of the system. In augmented coding, you care about the code, its complexity, the tests, and their coverage. The value system, he says, is similar to hand coding, tidy code that works. Karpathy draws it a third time in April 2026 with different vocabulary. Vibe coding raises the floor for everyone in terms of what they can do in software, while agentic engineering preserves the professional bar. 3 independent authorities, no shared employer, no common product to sell, same line in the same place. It converts neatly into policy. Name which mode a piece of work is in before the work starts. Throwaway and prototype work may be vibe-coded. Anything that will be maintained, operated, or depended upon is agentic engineering and is held to the handwritten bar. The failure organization's report is not choosing vibe coding. It is drifting into it without ever deciding to. Now the honest question, what does "I reviewed it" have to mean? The uncomfortable answer is that it cannot mean what it currently means for most people, because the feeling of having reviewed something is measurably unreliable. The Stanford study found participants with an AI assistant wrote less secure code and were more confident it was secure. METR found engineers who were slower believed they were faster. 2 rigorous studies, 2 different outcome variables, 1 structural finding. AI assistance degrades the accuracy of self-assessment. Your sense that you looked carefully is not evidence that you looked carefully. So "I reviewed it" has to become a claim about specific checks, not about attention. Here is the standard. You can explain what the change does, in your own words, without reading the diff again. You can say why this approach, and not the obvious alternative. You can point at the test that would fail if someone broke this next quarter, and if there is no such test, you said so in the pull request. You can name the failure modes: concurrency, partial failure, empty input, hostile input. And you know what happens at 3 in the morning when this pages, where it logs, and what you would check first. Notice what is not on that list: typing it. Plenty of code you are accountable for today was pair-written, copied from a wiki, or inherited from someone who left. The standard has always been that you can explain the change and defend it. Generation getting cheap does not move that standard. It removes one excuse, that you must have understood the code because you typed it. There is an extension to review scope that Agentic workforces, and it is easy to miss. In July 2025, a malicious pull request to the AWS Toolkit for Visual Studio Code repository carried a payload that was not code. It was English prose, a prompt instructing an agent to act as a system cleaner and delete local files and cloud resources. It was merged and shipped to the marketplace before it was caught. Per AWS, formatting errors in the prompt prevented the wiper logic from executing, and there is no evidence of customer data deletion. The lesson is about review reflexes. Every instinct a good engineer has is tuned to catch bad code. Nobody's threat model included, the malicious commit is a paragraph. So the surface you are accountable for now includes agent instruction files, tool configuration, and workflow definitions. If a file can change what an agent does, it is executable content, and it gets read like code. Then there is on-call, which is where accountability stops being abstract. The DORA research program, run by Google Cloud, surveyed nearly 5,000 technology professionals for its 2025 report. It found a positive relationship between AI adoption and delivery throughput and product performance, a change from the previous year, and a continuing negative relationship with software delivery stability. Their explanation, in their own words: AI accelerates software development, but that acceleration can expose weaknesses downstream. Without robust control systems, like strong automated testing, mature version control practices, and fast feedback loops, an increase in change volume leads to instability. Name the incentive, as always. DORA is run by Google Cloud, which sells AI coding assistance and also sells the testing, continuous integration, and platform products the report names as the fix. That is commercially convenient. It does not make the finding false, and the throughput up, stability down split cuts against a pure sales narrative. That split is the on-call story in one sentence. More change volume, the same or slightly worse stability, means more incidents per unit of time landing on the same rota. And here is what is genuinely new. An increasing share of what pages you at 3 in the morning is code nobody on the team composed line by line, some of it approved in a batch of 11 pull requests on a Thursday afternoon. One vendor dataset puts numbers on the shape of this. Pharaoh's AI, which sells engineering intelligence software, and therefore has an interest in you buying an instrument to watch the problem, published a 2026 report drawing on telemetry from 22,000 developers across 4,000 teams, comparing each organization's lowest adoption period against its highest. Epics completed per developer, up 66%. Monthly production incidents, up nearly 58%. Pull requests merged with no review at all, up 31%. Treat those magnitudes with suspicion. It is a vendor report, unrefereed, without confidence intervals, and highest versus lowest adoption period, conflates AI adoption with calendar time and everything else that changed. But the direction agrees with DORA, which is survey data from a different vendor using a different method. Two datasets that disagree, about a lot agree, that stability is where the bill arrives. So what does an accountable engineer do about on-call for code they did not author? 3 things. Merge in units you could debug at 3 in the morning. If an agent hands you a 900-line change spanning 6 subsystems, send it back and ask for it in pieces. Diff size is a reviewability property, and reviewability is an on-call property. Require that the change carries its own diagnostics, logging, metrics, an error path that says something specific. Agents will happily produce a bare catch block that swallows the failure, and you will meet that block again at the worst possible hour with nothing in the logs. And insist that whoever merged is on the hook, the merger, not the operator of the agent. If those are different people, the reviewer inherits the pager, and knowing that in advance changes how the review goes. Finally, attribution. Record AI involvement in the commit trail, a co-authored by trailer, a pull request label, something queryable. 2 real reasons. Forensics. When a class of bug is found, you want to ask which of our code was agent-authored and get an answer. And obligation. Some organizations and open-source projects now require disclosure. But be careful what attribution is for. It is a forensic marker, not a liability shield. The moment a trailer starts being used in incident reviews to explain why a human is less responsible, it has become the thing it was meant to prevent. Disclosure records what happened. Ownership does not move. The formal vocabulary is worth knowing, because it is what an auditor will use. The Open Worldwide Application Security Project, OWASP, lists excessive agency in its top 10 for large language model applications. That is the formal name for the situation where an action was taken and nobody can say who authorized it. If your process cannot answer that question, you do not have an accountability problem waiting to happen. You have one now. That is professional accountability, and it is entirely within your control. Legal accountability is not, and it is moving quickly. That is next. Chapter 17. Legal, Licensing, and Compliance. 3 pieces of housekeeping first, and they are not throat-clearing. They are the chapter. I am not a lawyer, and nothing here is legal advice. Everything here describes a status on a specific date, and the date is the 4th of August, 2026. This is the fastest-moving material in the course. If you are hearing it 6 months later, assume something has changed and check before acting. And where the research behind this course flagged something as unverified, I will say so out loud rather than rounding it up into confidence. 3 such moments are coming. I would rather you learn where the fog is than take away a tidy picture that is partly invented. Start with the litigation, because it is what people ask about first, and then I want to persuade you it matters less to your working life than the mechanics further down. The case that produced a doctrinal result is Bartz against Anthropic in the Northern District of California before Judge William Alsup, filed in August 2024. In June 2025, Alsup granted partial summary judgment holding that using lawfully obtained copies to train a large language model was fair use, and that retaining millions of pirated library copies was not, sending that portion toward trial on damages. In September 2025, Anthropic agreed to pay $1.5 billion, reported as roughly $3,000 per book plus interest, and described as the largest copyright resolution in United States history. In July 2026, final approval was granted by United States District Judge Arisley Martinez-Alguin. Some authors and publishers opted out in order to sue separately. Verification note said plainly, that procedural history reaches this course through an encyclopedic summary rather than the docket. The shape is well established. If the details matter to a decision, read the filings. The doctrinal takeaway is precise, and it is routinely mangled. The ruling separated training from acquisition. Training on lawfully obtained material was fair use on those facts. Retaining pirated copies was not. The money was for how the data was obtained, not for what the model learned. Anyone who tells you a court has ruled that training on copyrighted work is unlawful is collapsing two things the judge deliberately kept apart. The other case everybody names is Doe against GitHub, the class action over Copilot, filed in November 2022 in the Northern District of California by the Joseph Savary law firm. And here is the first fog bank. I could not verify the current procedural posture of that case. Not the surviving claims, not the appellate status, nothing from this year. So I am not going to state an outcome. If someone tells you confidently how Doe against GitHub turned out, ask them where they read it this month. What is safely citable is enough for our purposes. GitHub itself has acknowledged that a small proportion of the tool's output may be copied verbatim. The Software Freedom Conservancy, in June 2022, accused Copilot of ignoring code licenses used in training data. And in late 2022, Copilot was reported to omit Quake source code, with no author attribution or license. Those three facts are what the license contamination discussion actually needs, and license contamination is the part of this chapter that touches your job. State the risk precisely. A model may omit a non-trivial verbatim or near-verbatim span from copyleft license training data. If that span lands in a proprietary codebase, you have a license compliance defect. Not a lawsuit, a defect. Now state both halves honestly, because this is where the conversation usually picks one. The mechanism is real. The vendor concedes verbatim output occurs, and the litigated harm is, so far, theoretical. I found no documented case of an organization being successfully sued over a copyleft snippet emitted by a coding assistant. Both are true at once. Treat it as a defect class with real mechanics and an unproven claim history. The controls, in order of how much they actually buy you. First, turn on the vendor's duplication filter. The major assistants have a setting that blocks suggestions matching public code. Enforce it at the organization level, not per user, because per user settings are a survey of who read the onboarding document. Second, understand your indemnity. The major vendors offer intellectual property indemnification on enterprise tiers, and it is typically conditional on having that duplication filter enabled. The conditionality is where teams get caught. The indemnity is in the contract, and the filter is switched off in the console. Second fog bank flagged, I could not re-verify current indemnity terms for any vendor. Do not take a clause from me. Read your own contract and read the conditions, not the headline. Third, license scanning and continuous integration on every agent-authored diff, covering both the dependency manifest and, through code clone detection, copied source spans. It is a deterministic gate. It runs whether anyone is paying attention or not, which is why it beats a policy document. Fourth, a sentence that sounds too obvious to write down and is violated constantly in large monorepos. No agent-authored code goes into a project whose license you cannot state. Fifth, provenance metadata, so that if a contaminated span is identified later, you can find every place it landed. That is the commit trail marker from the accountability chapter, earning its keep a second time. Now regulation, specifically the European Union AI Act, which is the regulation people believe is coming for their coding assistant. The dates in force: 2nd of February 2025, prohibited AI practices and the AI literacy obligations. 2nd of August 2025, general purpose AI model obligations, governance bodies, penalties, transparency. 2nd of August 2026, general application of most of the Act, which, as I record this, is 2 days ago. Then the change most summaries have not caught up with. An amendment package, referred to as the AI Omnibus or Digital Omnibus, was proposed in November 2025, reached political agreement around May 2026, and entered into force on the 27th of July, 2026, according to the European Commission's own policy page. It delayed the high-risk obligations. Annex 3 high-risk systems, biometrics, critical infrastructure, education, employment, migration, and border control moved from the 2nd of August 2026 to the 2nd of December 2027. High-risk AI embedded in regulated products was extended to the 2nd of August 2028. Third, Fog Bank, and this one is important. Those omnibus dates come from a single fetch of the Commission's policy page, not cross-checked against the official journal. The direction, a delay to the high-risk obligations, is well established. The exact dates need verifying against the primary legal text before anyone relies on them. And here is the detail that makes the point. At the same moment, a widely used AI Act implementation timeline site was still displaying the original pre-amendment schedule. 2 reputable-looking sources, one of them stale. That is what a moving area looks like from the inside. Now the part that matters most, because the fear here is usually misplaced. An AI coding assistant is not, by itself, a high-risk AI system. Writing code is not an Annex 3 use case. The high-risk regime bites on the purpose of the system you deploy, not on the tools you use to build it. A great many engineers believe the opposite, and waste enormous effort classifying an editor plugin. What does apply to almost every team in the European Union is smaller and more actionable. Article 4, the AI literacy obligation, has been in force since February 2025. Providers and deployers must ensure staff have a sufficient level of AI literacy. That is live, not future, and a structured course of this kind is a plausible component of demonstrating you have met it. Second, the general-purpose model obligations on transparency and copyright policy flow down to you as a deployer through your vendor's documentation and terms, which means reading them. And third, the one to remember. If your team is building an Annex 3 system, the agent-authored code inside it is in scope of that system's technical documentation, risk management, and logging requirements. The tool is out of scope. The output is not. The practical control is unglamorous, and it is the first thing an auditor asks for. An inventory of which AI tools are used on which products, with a per-product classification. 4 other compliance surfaces people forget briefly. Data residency and confidentiality. Sending proprietary source to a third-party interface is a data transfer. Check your vendor's retention and training use terms per tier and whether regulated data may leave your jurisdiction. Enterprise tiers generally exclude customer content from model training. Verify per contract, do not assume. Secrets in prompts. A pasted environment file is a disclosure event whether or not the model retains it, and it belongs in your runbook with a defined rotation scope. Sector rules, which bite long before any AI-specific regulation does. Payment card standards, health information privacy rules, financial reporting controls, and the European financial sector's operational resilience requirements all impose change control and least privilege. An unsandboxed autonomous agent holding production credentials violates several of them today, with no new law required. If you need to persuade management to fund controls, this is the argument that works. And the management system standards. ISO IEC 42000 and one is the certifiable AI management system standard an enterprise will actually be audited against. The NIST AI risk management framework sits beneath it. Which leaves one honest observation to close on. As of August 2026, there is no finalized, certification-grade control standard specifically for using AI coding agents. The closest is a NIST effort to publish control overlays for securing AI systems, a concept paper in August 2025, an annotated outline in January 2026, with planned overlays covering generative AI assistance and single and multi-agent systems. It is in progress. You cannot be audited against it yet. So teams are operating ahead of the standards. That has one clear consequence. Your internal policy is doing work an external standard would normally do for you, which means it had better hold under pressure rather than being a document nobody reads. That is the next chapter. Chapter 18, Governance for Teams. One principle carries this entire chapter, and it was established back in Part 1. Advisory rules degrade, mechanisms hold. The vendor documentation says it more precisely than I can. Anthropic's own guidance for Claude Code notes that unlike instructions in a repository memory file, which are advisory, hooks are deterministic and guarantee the action happens. That is the whole design distinction, in one sentence, from the people who built both. The demonstration everyone remembers is the Replit incident of July 2025, where an agent deleted a live production database during a declared code freeze, having been told repeatedly, in capital letters, not to touch production. Treat that account carefully. The technical detail is single source, from the affected user on a low guardrail platform rather than a governed pipeline. But the lesson survives the caveats. I told it not to is not an access control mechanism. The absence of the credential is. So governance here is not a document. It is a set of places where the wrong thing cannot happen. Continuous integration gates, hooks, permission systems, credential scoping. Where something has to live in a document, I will say so and treat it as the weak form. Start with ownership, the one sentence that does have to live in a document. Write down that the human who merges owns the code, unconditionally. Alongside it, record a I involvement in the commit trail, a trailer, a label, anything queryable, so that when a class of bug turns up you can ask which of our code was agent-authored and get an answer. Attribution is forensics. It is not a defense. Second, review policy, differentiated rather than uniform, because a uniform policy is one everybody games. Human review is mandatory for anything touching authentication and authorization, cryptography, payments, personal data, infrastructure as code and continuous integration configuration, dependency manifests, and agent instruction files. That last category is the one teams forget, and the one that has actually been exploited. The reviewer must be someone other than the agent's operator. And here the policy has to get more specific than most policies do, because a measurement forbids the usual wording. The Stanford study published at the Computer and Communications Security Conference found that developers using an AI assistant wrote less secure code and were more confident it was secure. Against that finding, review carefully is not a control. It is a hope. Give reviewers a checklist scoped to the language, the weakness classes that actually bite in that stack, cross-site scripting for a front end, injection and authorization and cryptographic misuse elsewhere, and require them to state what they checked. A named check is auditable. Diligence is not. Third, the continuous integration gates. This is the deterministic layer, and it is the part of governance that does not get tired at 5 o'clock on a Friday. Blocking on every agent-authored diff, static application security testing, secret scanning with push protection, dependency scanning, license scanning, and a gate routing any new direct dependency to a human. That last one is cheap and defeats an entire attack class on its own, because slop squatting, where a model invents a package name, reproducibly, and an attacker registers it, only works if something installs the invented name without a person looking. Add lockful integrity, so a swapped package fails closed rather than resolving quietly. Turn install scripts off, because both major supply chain worms of the last year executed through install time hooks. Add a diff size limit that forces enormous agent pull requests to be decomposed, because a 900-line diff is not reviewable no matter what the policy says. And make the status checks required in a way a bot cannot bypass, with code ownership rules on agent instruction files, tool configuration, and workflow definitions. Unlike a prompt, a pipeline cannot be talked out of its position. Fourth, least privilege, scoped per session. Fine-grained tokens, single repository, read-only wherever read-only will do. No long-lived cloud administrative credentials in the agent's environment. Separate credentials for development, staging, and production, and the agent's environment simply does not contain the production one. Not the agent is instructed not to use it. Does not contain it. Fifth, sandboxing by default. Container or virtual machine, file system scope limited to the working tree, and the part people get wrong, egress allow listed by endpoint and method, not by domain. The reason is a finding from January 2026, when researchers at Prompt Armor showed that a product allowing outbound traffic only to a specific list of domains could still be used to exfiltrate a victim's files, because the vendor's own interface was on the allow list and it accepts uploads. An egress allow list is only as strong as the least restricted capability of the allow listed host. It is worth knowing what a mature harness gives you here, because it sets the bar for anything you build. Anthropic documents for Claude Code, read-only permissions by default, a working directory boundary, so the agent can only write inside the folder it started in. A sandbox shell tool with file system and network isolation. Fetching commands like curl and wget not auto-approved. Web fetches run in an isolated context window so fetched content cannot inject into the main one. Fail-closed matching, so an unmatched command needs manual approval. And trust verification on first run in a codebase and on new tool servers. And one documented caveat that inverts most people's assumption. Trust verification is disabled in non-interactive print mode. Your continuous integration usage, unattended, running on whatever content arrives, is your least protected usage. Govern it accordingly. Sixth, approval hygiene, framed as a security control rather than an ergonomics complaint. The practitioner version, from the same documentation. After the 10th approval, you are not really reviewing anymore, you are just clicking through. Prompt fatigue is a control failure. It follows, counterintuitively, that a team with 200 approval prompts a day has no approval control at all, and a team with 5 has a real one. Allow list aggressively and narrowly, so the prompts that remain are meaningful. Seventh, audit and logging. Log agent sessions, tool calls, and command executions. The tooling exists. Usage telemetry, configuration change hooks that can audit or block settings, changes mid-session, managed settings to enforce organization standards, audit logs for cloud sessions. The minimum viable audit answers 4 questions. Who ran an agent, in what repository, with what tools, and what did it execute? If you cannot answer those, you cannot run a post-incident review, only a discussion. Eighth, configuration as code. Agent memory files, tool server configuration, editor settings, and workflow definitions are security configuration. Version them, assign code owners, review changes, alert on drift. Not theoretical. The self-replicating package worm identified in September 2025 wrote rogue tool servers into local assistant configuration files, establishing persistence inside the developer's agent rather than the operating system. Very few teams do this, and it is the highest ratio of protection to effort on the list. Ninth, incident response for agent-specific events. Write the runbook before you need it, covering 4 scenarios. The agent executed a destructive command, the agent leaked a credential, the agent installed an unknown package, a tool server configuration changed unexpectedly. Define the rotation scope in advance and define it wide. Assume everything in the agent's environment is compromised. And know one thing that surprises people: editor checkpoints are not backups. They track changes made through the file editing tools, not through the shell. In the vendor's own words, this is not a replacement for version control. That is the control set. Now the shape it should take over time, which is staged autonomy. The evidence for staging is indirect but consistent. Mitchell Hashimoto describes a deliberate progression through 6 adoption stages, including phases that felt less efficient than working by hand. So adoption is a curve you have to be willing to pay for, not a switch you flip. And from the opposite direction, the vendor with most to gain from selling complexity is on record saying success is not about building the most sophisticated system, and that you should add complexity only when it demonstrably improves outcomes. The latter I am about to describe is my construction, not a documented standard, so treat it as a worked example rather than a citation. Level 0, read and plan only. The agent explores and proposes, it cannot edit. Level 1, edit in an isolated working tree, every change through review, no shell access beyond the test runner. Level 2, edit and execute inside a sandbox, network egress denied, full continuous integration gate on the resulting diff. Level 3, unattended runs in continuous integration, trusted input only, no secrets in scope, read-only token. Level 4, autonomous operation with authority over anything production adjacent, which for most teams should not exist. The rule for movement between rungs is the thing I would defend hardest. A team earns the next level by demonstrating the mechanism that makes it safe, not by demonstrating enthusiasm. You get level 2 when the sandbox is genuinely the default and the gates genuinely block. You get level 3 when audit logging can reconstruct a session. And one session-level rule sits across all of it. Meta's security team published a framework in October 2025 stating that an agent must satisfy no more than 2 of 3 properties within a session: processing untrustworthy input, access to sensitive systems or private data, and the ability to change state or communicate externally. Needing all 3 means it should not operate autonomously and requires supervision at minimum. Note, within a session, a fresh context window resets the exposure, which is why clearing between unrelated tasks is a security control and not merely tidiness. Meta calls the framework a stopgap until robustness research allows reliable detection of prompt injection, and calls the underlying problem a fundamental, unsolved weakness in all large language models. That is a frontier lab saying so in its own product security guidance. For a governance backbone with a name your auditor recognizes, OWASP published a top 10 for agentic applications in December 2025, developed with more than 100 industry contributors. I am not going to recite the 10 items because I could not verify the list and I will not invent it. Go and read it. You now have a policy. The next question is how to introduce it to an organization without the organization rejecting it. Chapter 19, Rolling it out without breaking things. Most failed rollouts of this technology are not tooling failures. They are measurement failures, sequencing failures, and one specific capacity failure that everybody walks into with their eyes open. Take them in the order you will meet them. Start with measurement, and start before you turn anything on, because otherwise you will never answer the only question that matters. Did this work? That is not managerial box ticking. We have a hard number for how wrong engineers are about their own productivity. In the METR randomized trial, developers who were measurably 19% slower believed afterwards that they had been 20% faster. Roughly 40 points of self-assessment error from experienced people on their own code. A team that rolls out agents without a before and after measurement is not gathering evidence. It is gathering opinions, and we know what those are worth. Now the honest complication, because it is the most underreported development in this field. In February 2026, METR published an update saying it was changing its experiment design. They had run a follow-up trial from August 2025, 57 developers, over 800 tasks, agentic tooling, and reported that the design had broken down. Why it broke down is directly useful, because your internal measurement will hit the same problems. Developers increasingly refused to participate at all because they did not want to work without AI, which removes the people who benefit most. Between 30 and 50% deliberately did not submit tasks they expected AI to be very good at, which removes the high uplift work. And timing itself broke because developers multitask while an agent runs. METR's own conclusion, in their words, based on conversations with study participants, they believe it is likely that developers are more sped up from AI tools now, in early 2026, compared to their estimates from early 2025. However, because of the selection effects in their experiment, their data is only very weak evidence for the size of this increase. That is intellectual honesty from the organization that produced the field's most quoted skeptical number. Take two things from it. Anyone still citing 19% slower as a present tense fact is misrepresenting the source. And your internal attempt will be worse than METR's, so design it knowing that. Practically, measure system outcomes rather than individual speed. Individual speed is where the bias lives. System outcomes are recorded by machines that have no opinions. And measure both halves, which is the part people skip. The DORA Research Program's 2025 report, from nearly 5,000 technology professionals, found a positive relationship between AI adoption and delivery throughput, and a continuing negative relationship with delivery stability. Their explanation being that acceleration exposes weaknesses downstream unless automated testing, version control and fast feedback rise with change volume. Name the interest. DORA is run by Google Cloud, which sells both the coding assistance and the platform products it prescribes as the fix. So your baseline needs throughput and stability together. Change volume, lead time, change failure rate, incidents per unit of change, and the one I think predicts everything else, time to first review and time to merge. Because here is the capacity failure you are about to walk into. You are increasing the supply of code without increasing the supply of review. Pharaoh's AI, an engineering intelligence vendor with an obvious interest in you buying an instrument for this, published telemetry from 22,000 developers across 4,000 teams, comparing each organization's lowest adoption period against its highest. Throughput rose. Median time to first review rose more than 1.5 times, average review time roughly tripled, and pull requests merged with no review at all rose by about 1/3. They call it the senior engineer tax. The security vendor Apiero saw it from another angle. A I-authored pull requests pack more change into fewer, larger diffs, which degrades reviewability directly. Treat those magnitudes skeptically, vendor telemetry, unrefereed, and comparing high adoption to low adoption periods conflates AI with calendar time. But the direction is corroborated by DORA's stability finding using a different method, and it is what the mechanism predicts. If review capacity is fixed and code supply doubles, review latency rises. That is not a study result, that is arithmetic. There is a real unresolved conflict here. DORA's thesis is that AI does not fix a team, it amplifies what is already there. Pharaoh's reports the opposite on this point. High-performing organizations in their dataset suffered the same deterioration as everybody else. Survey data versus telemetry, and they disagree. That is not settled. My working position, labeled as inference. Review capacity is a hard constraint that good practice postpones rather than removes. So plan review capacity before you plan adoption. Diff size limits that forced decomposition, small batches as a stated norm, and review latency as a first-class metric that someone owns. Now the metrics you must not use, because each will actively mislead you. Lines of code. Wrong as a productivity measure for 50 years, but it returns in a new costume here, teams estimating agent cost from diff size. An agent that retries, rereads files or loops burns tokens with nothing to show for it. Cost is a function of convergence, not diff size. Acceptance rate. Tempting because the tools report it. But ThoughtWorks field notes point out that acceptance metrics miss real value, since a developer can benefit from generated code they then discard. And Pharaoh's reports acceptance climbing from 20 to 60% across their window, which tells you the suggestions got more usable, not that the output got more valuable. Pull requests merged. Useful, but never alone and never as a target, the best available Agentic rollout study measures exactly this, and its authors flag the limitation themselves. A merged pull request is not the same as the value it delivers. Next, sequencing. Adoption is staged, and each stage is earned. The prerequisite is not tool selection. It is control system maturity. A team with weak automated testing, immature version control, and slow feedback does not get a productivity win from agents, it gets a faster route to instability. DORA's capabilities model names 7 practices that magnify AI's positive impact. The two to act on immediately are strong version control and working in small batches. A third, a clear and communicated I stance, matters more than it sounds, because a stated policy is what lets people experiment openly instead of quietly. Then move teams up the autonomy ladder by mechanism, not by enthusiasm. A team gets sandboxed execution when the sandbox is genuinely the default. It gets unattended continuous integration runs when the gates genuinely block and the audit log can reconstruct a session. Each gate is a thing you can point at. Expect the early stages to feel slower, because they are. Mitchell Hashimoto's account of his own adoption describes deliberately pushing through phases that felt less efficient than working by hand. If your rollout plan contains no period of negative return, it is not a plan. It is a forecast. Now training, where most programs go wrong. They teach prompting, the fastest decaying knowledge in this field, since a trick that mattered in one model generation is folklore in the next. Teach verification instead, because verification is invariant. 3 things I would put in a curriculum. Teach the known failure modes as labs, so people have watched an agent fail in a controlled setting. There are reproducible ones. A harness misdetecting the context window and compacting far too early, which users experience as it keeps forgetting. A translation layer corrupting tool calls, where the same model went from 10 valid calls out of 10 to 0 out of 10 once a transformer was enabled. Malformed tool calls poisoning the conversation history so later calls imitate the error, which recovers by truncating history rather than by retraying. Someone who has seen these stops overtrusting the tool without being lectured. Teach cost as an engineering property. Verifying that your cache is actually being hit, token pre-flight checks, routing cheap work to cheap models, batching anything not latency sensitive. And teach the harness engineering habit, the most transferable practice in the corpus. Hashimoto's version, whenever he sees an agent do a bad thing, he makes an earnest effort to prevent it from ever doing that bad thing again. Treat every agent failure as an environment bug rather than a prompting bug, and encode the fix where the agent will meet it. Repository instructions, hooks, tests, tool permissions, rather than in the operator's head. Finally, what organizations report actually working, and the failure modes to avoid. The most directly relevant evidence is a study of Microsoft's early 2026 rollout of command-line coding agents across tens of thousands of engineers over 4 months. Adopters merged roughly 24% more pull requests than they otherwise would have, and the lift persisted across the whole window rather than fading as a novelty effect. It is not randomized, adopters self-select, and it is Microsoft authors on Microsoft products. Treat the magnitude accordingly. The finding I would act on is not the number. It is the mechanism of spread. Adoption traveled primarily through social networks, and seeing a peer use, it was the dominant route to first use. Which gives the first and most common rollout failure mode. Do not mandate usage. Mandates produce compliance theater, metric gaming, and a population who use the tool once, badly, and now hold a firm opinion. Fund visible practice instead. Internal demos, recorded sessions of real work including the failures, a channel where people post what did not work. Peer visibility is what moves adoption, so buy more of that and less enforcement. The second failure mode is measuring the wrong thing. If your dashboard shows lines of code and acceptance rate going up, you have built a machine for feeling good. The third is ignoring the review bottleneck, and I will repeat it because it is the one that damages teams. Double the code and do nothing about review, and you have not removed a constraint. You have moved it onto your most senior people, who were already the constraint. And a fourth, financial rather than technical. Measure your real token consumption per task through metered pricing at least once, even if you buy seats. Subscription pricing is a promise, not a cost floor, and a capacity plan built on seats is an unhedged position on someone else's pricing decision. That is the rollout, which leaves the harder question, 3 parts on, whether any of this is right and what would show that it is not. Chapter 20, the verdict 3 parts on. 3 parts, 1 governing instinct throughout. Here is my model, here is the evidence, here is what would change my mind. This chapter is the 3rd part of that sentence, the part most courses skip. First, the throughline restated, because a verdict on a thesis you cannot remember is worthless. The first claim is that the capability change is real and recently dated. 2 credible, independent observers put it in the same 8-week window. Andrej Karpathy, in February 2026, wrote that programming had changed not gradually, but specifically that last December. And that, with asterisks, coding agents basically did not work before December and basically work since. Simon Willison, independently, named a November 2025 inflection point, where the models tipped across an invisible capability line and a set of harder coding problems opened up. Different people, different evidence, same window. That is why a genuinely excellent engineer can be fluent in software and illiterate in this. And the counterweight, carried through all 3 parts and not dropped now. METR's randomized trial found experienced developers 19% slower, while they believed they were 20% faster on pre-inflection tooling. In February 2026, METR said that design had broken down, that developers are probably more sped up now, and that its own new data is only very weak evidence for the size of the increase. So the honest statement is neither agents make you faster, nor agents make you slower. The magnitude is unknown, and the perception gap, roughly 40 points of self-assessment error, is the part never retracted. The second claim is that the vocabulary is simple ideas wearing intimidating names. A context window is a working set. Context engineering is curating what is in it. A harness is the environment the model runs inside, tools, permissions, the loop. And the distinction that matters most is the plainest. Workflows orchestrate models through predefined code paths, agents direct their own processes and tool usage. None of it is harder than a build system. The third claim is that context is the binding constraint, architecturally rather than incidentally. A transformer requires every token to attend to every other token, producing n-squared pairwise relationships for n tokens. As the window fills, recall degrades, that is context rot, and it is why a larger window does not straightforwardly solve the problem. Compaction, note-taking, subagents with clean context windows, just-in-time retrieval. 4 techniques, 1 constraint. The fourth claim is that verification is the discipline. The highest leverage practice in the corpus is to give the agent a way to verify its own work, because the agent stops when the work looks done, and without a check it can run, looks done is the only signal available, and you become the verification loop. On Backbench, which tests security by running real exploits against generated backends, the best model at the time scored about 62% on correctness, and roughly half of the functionally correct programs still had working exploits, about 31% correct and secure. And across more than 100 models, Veracode found that while functional correctness improved, security performance remained flat regardless of model size or training sophistication. Security is not on the capability curve. The next model will not fix it. Engineering will. The fifth claim is that judgment got repriced upward. Writing code is cheap now, so the scarce resources are review, verification, and judgment. Karpathy's version, you can outsource your thinking, but you cannot outsource your understanding. That is the thesis. So what would falsify it? Not, what would make me uncomfortable? What specific, observable result would make me say the model was wrong? 1. A rigorous post-inflection randomized trial developer-level randomization, experienced engineers on their own mature codebases, agentic tooling, measuring time to a correct and mergeable change, finding no benefit or a persistent penalty, and then replicated. That falsifies the capability claim as I have stated it. METR is redesigning toward exactly this, so the result is checkable within a couple of years. 2. Security climbing with capability. Repeat Veracode's method across the next 100 models and find the failure rate falling materially, a trend, not a point or two. That falsifies, security is not on the capability curve, and turns much of Part 3's security doctrine into expensive overengineering. Though I would want two independent replications, since a vendor that sells scanning is not the ideal source for news that scanning matters less. 3. A prompt injection defense that holds under adaptive attack. The paper called "The Attacker Moves Second" reevaluated 12 published defenses that had reported near-zero attack success. Against attackers who knew the design, most fell above 90%. If a defense survives that treatment, evaluated by someone other than its authors, then my position that this is access control rather than input sanitization is wrong, and the architecture chapters need rewriting. 4. Longitudinal maintainability data from a source that does not sell the measuring instrument, showing duplication, churn, and refactoring flat or improving under heavy agent use. That falsifies the code quality worry, which rests on vendor telemetry. 5. Prices. If metered prices rise sharply or subscription caps tight until the cost per completed task exceeds a loaded engineer hour for that task, the economic case inverts. 6. Entry-level employment recovering. If the Stanford payroll series shows the 22 to 25 cohort in exposed occupations returning to trend while adoption keeps climbing, the juniors' problem was a moment in one labor market rather than a structural break. And one that cuts the other way, because falsification is not only for the optimistic half. If heavily agentic teams showed measurably lower defect escape rates than handwritten baselines, my insistence that the verification stack is the expensive part would be wrong. Now the strongest critic at full strength. Baldur Bjarnason, an Icelandic developer and researcher, wrote a piece in March 2026 called "The Two Worlds of Programming." And it is the best critique in the field, not because it says the tools are bad, but because it explains why the argument never resolves. Optimists and skeptics observe the same thing, that these models scale up existing practice and reach opposite conclusions because they disagree about whether that practice was any good. In his words, there is nothing either group can say to the other to shift their opinion, because the disagreement comes down to a fundamental difference in worldview. And his own side sharply. When developers say models make them more productive, keep in mind what they are automating: dysfunction, tampering as a design strategy, superstition-driven coding. Take that seriously, because it is not about capability. It is about measurement validity. Gains measured against a baseline nobody has established was good. That argument survives every model improvement. My response is a response rather than a refutation. The same reasoning cuts both ways. If the baseline really is that bad, tooling that raises the floor is a gain, not a loss. And the premise, an industry in compounding crisis, is asserted in that piece rather than demonstrated. So I present it as he does, a clash of priors, not a settled finding. Two more, briefly. Armin Ronescher, creator of Flask and an enthusiastic agent adopter, which is what makes him awkward to dismiss, argues that large projects were never limited only by how fast an individual produces code, but by how well people coordinate their understanding. Agents remove that friction, and so, in his image, the tower does not fall and we do not notice what was lost. It just keeps rising. Nobody has measured that, and he would say so himself. And Ed Zitron, whose case is that the pricing is a capital market subsidy rather than a business. Name his incentive as I have named everyone's, a professional critic whose livelihood is built on the bubble thesis, exactly as a vendor's is built on the opposite, working mostly from other people's figures. But one claim is checkable arithmetic rather than forecast, that you can burn $14,000 of tokens on a $200 a month subscription. If you sized your budget on seats rather than metered tokens, you hold a position you do not control. Which brings me to what is genuinely unresolved. 3 things I will not pretend to settle. The sustainability of pricing. Nobody outside these companies knows the gross margin on inference. No vendor publishes unit economics. Every claim that inference is sold below cost is inferred from capital expenditure and revenue, not disclosed numbers. What we can say is that prices have fallen repeatedly, capital commitments are enormous, and pricing is a variable you do not control. The longitudinal quality question. No published defect escape rate study tied to a AI-assisted authorship. No review burden time study. No post-inflection randomized trial. No measurement at all of what Ron Escher describes. And the best-known maintainability dataset comes from a vendor that sells the instrument for detecting the decline it reports. That is not a good evidence base, it is the one we have. And whether prompt injection is solvable at all. Meta's own security team calls it a fundamental, unsolved weakness in all large language models and frames its mitigation as a stopgap until robustness research catches up. The researchers who describe the failure as role confusion expect injection defense to remain a perpetual whack-a-mole game unless models acquire genuine role perception. Against that, the CAMI-L work shows the problem is tractable architecturally, about 77% of benchmark tasks solved with a provable guarantee, against 84% undefended, so roughly a 7-point utility tax for provable security. Unsolved at the model layer, manageable at the system layer, at a measurable cost in autonomy. Whether the model layer can ever be fixed, nobody who has published on it knows. So, the close, I will not hand you a verdict to adopt. A verdict adopted from me is worth nothing the moment the ground moves again, and on the evidence of the last year it will. What I hand you instead is a standard. Name the mode before the work starts. Vibe coding for throwaway work, agentic engineering, held to the handwritten bar, for anything that will be maintained or operated. Drifting between them without deciding is the documented failure. Put your controls in mechanisms, not documents. Advisory rules degrade under deadline pressure. Continuous integration gates, permissions, and sandboxes do not. Trust instruments over impressions, because your judgment about AI output is measurably miscalibrated, and that is not an insult. It was measured on people exactly as experienced as you. Keep a category of work you do by hand and defend it. And be able to explain and defend every change with your name on it, whatever produced the diff. That standard does not depend on which model is best this quarter or on whether my falsifiers land. It is portable, and it is what I would want a certification in this field to certify. One last request, meant as respect rather than flourish. Go and check the dated claims in this course, Carpathy's December. The 19% its own authors have qualified. My 6 falsifiers, written to be checkable so you can hold me to them. If one has broken, believe the evidence and not the course. That is the whole discipline, and it is the last thing I have to teach you. Thank you for listening.